Balancesin চালছে না আর কোন সরি ব্রেকে টপ কথা বলি আর দশটার বলি আর বসে মোহন দেশর টাইম ଥିଲା তো 10টা ବେଳେ ଅପେକ୍ଷା କରିଛି ତ ହଁ ହଁ Good morning, Dr. Mantes.
Hello. नाम पत्र ग्रहण कर लिया अरेस्ट करने ठीक
Good morning, Dr. Mantes.
Good morning. I don't have my camera for some reason.
Hello, good morning.
Hello.
Good morning, sir. Can you hear me?
Yes,
Yeah, I can hear you, but you cannot hear me clearly. Let me see.
Okay, no problem. No problem. So the first session is going to be Professor Ram Mohammed, right?
But the camera is, I cannot turn it on. Somebody else has to do it, probably.
Anuradha, ready to start?
Yeah, I'm ready.
Are you able to?
We can start.
Dr. Mantes is also ready to wait.
Let me see. Where is my? Okay, can you see my talk?
Sir, just a second, please, sir. Wait.
So, whom are you going to start now?
Sir.
But can you see the file?
Oh, sir. Okay. Okay, I can.
My
Okay, a
problem
very pleasant morning.
How do I access my talk? Well, the camera is not. Well, somebody else controls the camera? Can you listen to me?
Sir, yes, it's audible.
But where is the camera? Can you see me?
No, sir. Sir, you please on your camera, sir.
I'm trying to switch it on, but it doesn't do anything in my side.
Okay. Sir, can we start with other one? In between
Yes.
that, if you will be ready, so can we start with other one?
Yeah, sure. Go ahead.
Okay. Thank you, sir. A very pleasant morning and a heartfelt namaskar to everyone present here and a warm welcome to virtual participants and eminent online speakers. I am Dr. Anuradha Sahu from the Department of Mathematics, Shiksha Anushandhan University. And it is my immense pleasure to welcome you all to the second day of the 4th International Conference on Applied Mathematics in Science and Engineering, AMSE-2025, being held from 28 to 30th August 2025. This conference is organized by the Department of Mathematics ITR Shiksha Anushandhan University deemed to be University Bhubaneswar in collaboration with the Department of Mechanical Engineering NIT Arunachal Pradesh. We are delighted to have your gracious presence as we begin another enriching day of technical deliberation which will be conducted in the online mode. Today we are indeed privileged to have with us Professor Swarup Nandan Bora from the Department of Mathematics IIT Guwahati, who will be the chairing this technical session. Professor Bora is an internationally acclaimed researcher in ocean engineering and differential equation. He has published over 140 research papers, guided numerous PhD scholars, and delivered more than 200 lectures worldwide. He has also held several key academic and administrative positions, including serving as the president of the Indian Society of Theoretical and Applied Mechanics in 2022. I now take the pleasure of inviting Professor Swarup Nandan Bora to kindly conduct and carry forward the proceedings of this technical session. Sir, please.
So good morning everyone. So welcome to this technical session. So we have three speakers. I think Professor Mahapatra is having some problem in connecting to us. So we'll start with the lecture which is scheduled second, which will be by Dr. Mohantes Vasavarajappa. I hope you are there. Mohantes Vasavarajappa?
Yes, sir. I'm available.
Yeah. So it seems just looking at his profile, he's a very young faculty member in Texas A&M International University. He did his PhD from Kuvempu University and he did his PDF in UTRGV. I think that is University of Texas, Rio Grande Valley, right?
Yes, sir. You're right.
Yeah. So I have a very close friend there, D.D. Bhatto. He was my senior. You must have known him or met him.
He was my supervisor in the postdoc.
Is it? Okay, he was my senior in PhD. Okay, anyway.
That one.
So, although very young, he has already established himself in fluid dynamics, especially his works on instabilities. And I have observed that he has some very good publication, including in journals like Physics of Fluids and International Journal of Heat and Mass Transfer. So without further delay, so I'd like to request Dr. Mohantes Vasavarajappa to start his lecture. So is it okay if I give you 25 minutes, then we can give 5 minutes for questioning?
Yeah.
Okay.
Yes, that is fine.
Thank you for joining online. It's already very late there, I guess. Must be around midnight, right? Yeah.
No, it is 12 o'clock now. It is fine. But I just need a confirmation. Do you see my screen, sir?
Yeah, if you make it full screen, otherwise you can see. Yeah, now it's fine. If you please start. Thank you.
Oh, okay. Thank you so much, sir, for the wonderful introduction. I would like to thank the organizing committee for the invitation, specifically Professor S.R. Mishra ji and Ram Prakash Sharma ji from the NIT Arunachal Pradesh. So they are my very close friends and as well as my mentors. Today I will be talking about frontiers in fluid instabilities from viscoelastic bifurcations to nanofluid dynamic. So let me talk about little bit of my background. In the introduction, they already mentioned I did my master's, bachelor's, and PhD from Kuvempu University, And then I started my work at Christ University as an assistant professor from 2016 to 2021. And in the year 2021, I joined the University of Texas, Rio Grande Valley, to pursue my postdoc. And then now currently I'm an assistant professor at Texas A&M International University. So in this talk, I will be talking about, I will introduce two projects, two of my projects basically. In the first project, it is a joint work with Dr. Dambaru Bhatta. He was my postdoc mentor at UTRGB, a very kind person, and he helped a lot in, when I was there in the UTRGB. So this project is about nonlinear stability analysis of reliever and convection problem for the viscoelastic type of fluid, specifically Navier-Stokes white fluid model. So before I jump into the project, let me provide some motivation, and then I will start the project one. So the Bernard convection problem, as we all know, it is the type of flow which is driven by the temperature gradient. So in these problems, we have a couple of research questions which are very, very important in technical applications and in various industries and as well as in science. Specifically, what is that critical temperature gradient will trigger the instability, and how do fluid properties influence the onset of instability, and how does the geometry of the flow medium also impact on the instability. So these are the main and critical research questions in reliever and convection setup of a problem. In the analysis, we come across a dimensionless Rayleigh number. So this number will help us to answer all of these three questions. Like, it will allow us to study how fluid properties will influence the onset of instability. It allows us to study how critical temperature difference will cause the instability, and also the flow medium. For a classical problem, this is the threshold value for the reliever and convection problem. That is for the rigid boundary conditions. Now I will be showing some animations which I have taken from this source. This is when Rayleigh number is equal to 1000, there is no onset of convection basically. So we have no fluid motion, but there is only heat transfer only in the upward direction. As you can see, we are providing the heat from the bottom. We are cooling the layer from the top. There is some critical temperature difference, but that is not sufficient to trigger the instability. So we have no fluid motion. The fluid is still stable now. So when Rayleigh number is equal to 1800, so that crosses the threshold value. It is a little bit higher than the threshold value. As you can see, there is a commencement of convection and also the movement of the fluid. As you can see, the formation of Bernard cells in the flow system. For the very large number of Rayleigh numbers, the convection turns out to be turbulent. So in the previous case, we have a convection, but it is a laminar convection. Because if you look at the two cells, these two, the parcel of the fluid in one cell is not interacting with the other one. So still the flow is laminar in this case. When it comes to this one, we have a turbulent convection. So this is at the very high Rayleigh numbers. The another motivation for this project is would be the fluid model, that is Kelvin-White fluid model. It used to be used to describe the the solid materials before, and it also describes the fluids with both viscous and elastic properties. Now, this model has applications for polymer solutions, biological fluids, and geophysical laws. For the incompressible fluid, the governing equations for Kelvin-White fluid model will be given here. So this is pretty much same as your Navier-Stokes equation, in addition to the Kelvin-White fluid term here. So that is lambda times gradient of T, Laplacian of U we have. So this will provide the elastic responses of the fluid model. where lambda is the elastic modulus coefficient, or it is also known as void coefficient. So this system was, investigated by the Russian researchers, mainly Oskolov and et al. They pointed out that this term will act as a very good regularization term in the Navier-Stokes system. So there are also some studies in they have a Kelvin-White fluid model term in the energy equation as well to improve the the regularity of the solution. So how to see this equation as a momentum balance equation? So we have a momentum balance equation here where sigma ij is the Cauchy stress tensor, where dot denotes the material derivative. So for this model, the sigma ij will be given in equation number 1. So we have the Kelvin-White fluid term here. Still, if you see, we have a local time derivative. So that is what it was noticed by the Damis here. It is not the objective derivative; it is a local time derivative. So in the study by Pawlowski, so he proposed the model to describe the water containing the weak polymer solution as given in equation number 2. Still, we have the the time derivative, but it is not still an objective derivative. But there was a model by the Walters and Beard, so that is known as elastico-viscous fluid, that is given in equation number 3. Still, there are some studies, they have used the model number 1 to conduct the linear stability analysis, and that is going to be a sufficient model when we conduct the linear stability analysis. So it was, recently studied by the Professor Brian Strogan. He made a number of studies by utilizing the model number 1, even though we have a local time derivatives in the Cauchy stress tensor. These are the some of the studies by the Brian Strogan, and that will lead us to a motivation to conduct this research paper. And there are you could find tons of papers on Kelvin-White fluid model, and also a separate the monograph in this particular book by Brian Strogan, where he had mentioned the several fluid models involving Kelvin-White fluid model, and also the applications of that model. So this is the physical geometry of the problem, the current project. That is, we have a fluid layer between the two plates. We are heating the fluid layer from the bottom, and we are cooling it from the top. We are also salting the layer from the bottom, and we have a solute concentration of the top that is going to be Cu. So in this system, we are heating the fluid layer and as well as salting the layer from the bottom. So we have a stabilizing mechanism and as well as destabilizing mechanism. So there is a clear competition between stabilizing and destabilizing mechanisms. So this will give us very interesting results. So gravity acts vertically downwards, and we have taken these two layers to be relatively large, sufficiently large along x and y direction, and the distance between the two plates is going to be h, and that is in the z direction. So for this system involving the Kelvin-White fluid term, the governing system looks like equation number 4. So we have a conservation of mass equation, the Navier-Stokes equation involving the Kelvin-White fluid term, and the conservation of energy and conservation of salt concentration. You notice here we have a term that is called as a Soret term, or it is also called as thermodiffusion term in the salt concentration equation. We have assumed that Oberbeck-Boseniak approximation to construct this model. What it means is the density is treated as constant everywhere except in the buoyancy force term, or when it is multiplied with the gravity. So the density is defined in terms of temperature and as well as salt concentration. That is a linear form, which is given here in the orange color equation. And the relevant boundary conditions and the domain for the problem are given here. And I have assumed that no slip boundary conditions on both the walls. And we have taken isothermal and isosolutal boundary conditions at both the walls, basically. And we also assume that the TL is larger than TU. That indicates we are eating the layer from the bottom. And also we assume that CL is greater than CU. That indicates we are salting the layer from the bottom again. Now, to study the stability of the problem, we initially find the basic state solution. That is, I showed you the first animation where there is no motion of the fluid basically. So let us find the basic state solution. That is also known as conductive state solution, where there is no motion of the fluid. And as you saw in that animation, the heat transfer occurs only in the z direction. Analogously, even the mass transfer as well, like the salt concentration profile. So we are going to assume T is only function of Z in the basic state, and salt concentration is also a function of Z alone. So plugging these back to the governing system, we get the following ODEs and with these boundary conditions. So solving these differential equations, we get the basic state solution. We have a basic state solution in equation number 7 now. So our goal is to study the stability of the basic state solutions, and that we do by imposing some small perturbations with the finite amplitude, and we see how those perturbations grow in time. So in this study we did linear and nonlinear stability analysis by introducing the perturbations as given in 8. So these perturbations are assumed to be periodic in nature, both in x and y direction, and they have a finite amplitude. So with the help of these perturbation variables and also some scaling variables, we get the dimensionless perturbed system as given in 9 and with the boundary conditions as given in 10. So we have some number of dimensionless parameters. Among them, the Rayleigh number that is given in RT is our, the point of interest basically. Now we have some parameters here like Prandtl number, Kelvin-White fluid parameter, Ekman damping parameter, salt, Rayleigh number, Lewis number, and Soret number. So these are the other physical parameters of the problem. So we do the linear and nonlinear analysis. So we follow the standard procedure of linear stability analysis. We assume the the perturbations are very small. So we linearize the system by neglecting the nonlinear terms. We eliminate the pressure gradient term, and we apply the normal mode approach because we assume that the perturbations are periodic in nature, x and y direction, and also the resultant system will be linear. So that will allow us to do the normal mode approach. So considering the normal mode approach, we get the differential eigenvalue problem as given in 11. And we need to find the Rayleigh number RT that satisfies the system basically. And we have a K square, this is the total wave number. And once I have the Rayleigh number, I have to minimize the Rayleigh number with respect to the total wave number. And that will give us a threshold value from the linear stability theory. Now I will move to the nonlinear analysis. We mainly use the energy method to conduct the nonlinear stability analysis. Again, so this is a wonderful book if somebody is interested on energy method and stability analysis of the nonlinear theory by Brian Stragon. So there are a number of illustrations, number of examples, and a number of the problems in great detail. So in the energy method, we construct the energy identities. Basically, what we do is we take the dot product of velocity perturbation to the momentum equation of the perturbation equation, and you multiply theta and then you multiply phi to the perturbation equation, and then integrate the equations over the volume or over the domain. So that leads to the following energy identities. So we have the energy identities which are given in 13, 14, and 15. Here we have a L2 norm, and as well as we have a inner product notation. And with the help of these energy identities, we also construct the energy function as follows. If you look at this energy function, it looks like we have a sum of kinetic energy and potential energy. So kinetic energy will be by the momentum perturbation, like we have half velocity square. In addition to that, we have like the velocity gradient square as well. And we have some potential energy which is caused by the temperature perturbation and as well as salt concentration perturbation. In this energy definition, we have eta 1 and eta 2, they are coupling parameters, and we have to be chosen optimally to have a better threshold values. And differentiating this equation, we get the differential equation in terms of for the total energy function. And if you see these terms, they're basically the left-hand side terms of these equations, like identities 13, 14, and 15, which we got from the perturbed system by doing some math. Now, we can just add these equations, multiplying eta 1 to the 14 and multiplying eta 2 to the 15. So that will give us a energy equation as given in 17. So with the two important terms here, that is the dissipation term and the production term. So it's a positive definite term, and with the negative sign, like it dissipates the energy. And we have non-positive term here, so that will, like reduce the energy basically. Now again, there is a computation between these two terms. So whichever wins, we can see how the energy grows, how the total energy of the perturbation grows as time progresses. So we recast the equation as given in 19, and we introduce the 1 by RE as maximum of I over D, where H is the space of admissible solutions. With that introduction, that energy equation will become inequality as given in 21. And see that it is positive, then you see we have energy function which decays basically because we have a negative term on the right hand side essentially. So the condition is if RE is greater than 1, so this factor will become positive. Now, with the help of Poincare inequality, we can deduce that D is greater than pi square times B times energy function, where B is minimum of all these quantities. So the energy equation, energy inequality turns out to be inequality what we have in 23. Solving this equation for energy function, we get the total energy function which is going to be less than or equal to E of 0 exponential of negative this quantity. And what we have inside all our positive definite terms. So what we can conclude is the total energy of the perturbations will decay exponentially fast for all the initial data what we provide. Okay, provided the condition is RE must be greater than 1. Like we can compute the RE, R sub E, by this maximization problem. So what we have in the equation number 20. So now our goal turned out to find out this condition like the RE value by solving that maximization problem. So solving the maximization problem by using the calculus of variables and introducing the Lagrange multiplier for the incompressibility condition, we get the following system that is given in 25 from the nonlinear theory. Again, applying the normal mode approach, so we have the differential eigenvalue problem again, where RT is the eigenvalue, and these are the corresponding boundary conditions for the system. So you remember, we have two coupling parameters, eta 1 and eta 2, and I told you in the beginning we have to choose them optimally well. So the threshold for the nonlinear theory will be this. So we have to maximize the Rayleigh number with respect to coupling parameters, eta 1 and eta 2, and we have to minimize with respect to the total wave number. So that is going to be the threshold value from the nonlinear theory. And we solved this eigenvalue problem by using Chebyshev spectral collocation method for the eigenvalue RT, and we got very interesting results. I will present some results now. So this is the neutral stability curves for both linear and nonlinear theories. You see that we have a blue line from the linear theory, and the red curve is from the nonlinear theory. there is a clear gap between the threshold values from the linear theory and non-linear theory. So that indicates that there exists a subcritical instability region. Okay, so that is denoted in this shaded region. So we have some subcritical instability region. So there we don't know the stability of the system. But what we know is from the linear theory, the any really number above this blue line, the system is going to be unstable. Whereas from the nonlinear theory, so nonlinear theory will provide the threshold for the stability of the system. So any really number below this red line will, the red curve will ensure the system's stability. But in the subcritical instability region, we do not know, the status of the stability of the system. It can be stable or it need not be, stable. So it need a rigorous, investigation in this region basically. So now I will draw your attention to the results of the threshold values for the variation of Kelvin-White fluid term. So this is our key parameter in the problem. So we wanted to see how the Kelvin-White term will impact the stability of the system. Now, as you can see, we are finding the Rayleigh number with respect to the solute Rayleigh number. For a small values of solute Rayleigh number, the convection occurs only in the stationary mode, not in the oscillatory mode. Okay. Whereas for some larger number of the solute Rayleigh number, the onset of convection is going to be by oscillatory mode. You see these curves; these are from oscillatory mode of convection. And also one can see that as I increase the values of the lambda, that is, as we strengthen the Kelvin-White coefficient, the threshold value also increases. So indicating that stabilizes the system. So the Kelvin-White fluid term or the viscoelastic behavior of the fluid will help us to stabilize the system. Okay, so that is what we are observing from this plot. And this plot is also plotted for two different values of Soret number. So the left-hand side plot is in the absence of Soret effect, and this one is in the presence of Soret effect. Again, you could see the threshold values are smaller when Soret number is present, indicating that the Soret number has a destabilizing impact on the system. So I have some plots for Ekman damping parameter. So we have some plots here. So the left-hand side plots, what we have on the left, they are in the absence of Ekman damping, and this is in the presence of Ekman damping. As you can see, if you look at the values in the presence of Ekman damping, the fluid system is going to be stable. As you can see, the values, the magnitude of the velocity contour plots, that is the velocity perturbations, they are smaller when the Ekman damping is present, which means that it acts as a stabilizing agent in the fluid system. So that is the impact of the Ekman damping in the fluid model. So we did similar works in the same direction by considering the Kelvin-White fluid model with the different setups. This study is about the magneto-LTNE porous convection problems. The previous problem is in the classical Rayleigh-Benard convection setup. So whereas in this problem we did a stability analysis in the porous media, and specifically by considering local thermal non-equilibrium model and in the presence of magnetic field. So to see how they impact on the fluid system, the stability of the fluid system. So in this model, in this work, specifically we have chosen some practical materials like two porous materials, Sander sandstone and aluminium metallic foam. And we performed a similar analysis.
Hello.
Yes, sir.
Can you please complete in 2-3 minutes?
Yes, I will wind up. Yeah, thank you. So whereas in this study, we again performed the similar sort of analysis but we did included some specific fluid, porous materials with the same fluid model. We also observed very interesting results in this article. And in some of my other work, like it is also again with my mentor Dr. Dambaru Bhatta. So in this study, we accounted the viscoelastic fluid model. So in this case, we have used the third grade fluid model where it has applications in polymers. And recently, we did a penetrating convection problem where the convection occurs by the internal heat source term. With this, I would like to stop my talk, and I'm happy to answer if you have any questions and queries. Any questions, any comments, or any queries? I would be happy to help you, and or maybe to answer if you have some questions.
So are you done?
Yeah. So I
just wait if someone has any questions. I'll ask. Does anyone have any question? We have 2-3 minutes left. Audience. Yeah, you have to come here. You just wait. There is one person who will ask you a question. I have one or two, but maybe I'll discuss it later.
Oh, okay. So glad to know that you're he's your senior, and nice to meet you, sir.
Yeah, when I joined PhD, he had just completed his second year, and he was kind of my mentor because he's much older than me. Anyway, there is one person who will ask you a question.
Yes, sir. Go ahead.
Sir, you are working on the nonlinear stability analysis.
Yes, sir.
But in your nonlinear stability analysis, there is no eigenvalue problem. There is no term of Kelvin void parameter. How you justify it?
Yeah. So that is a very good question. If I see the eigenvalue problem in 26, we don't have some parameters which are in the the time dependent term. Like we have a Kelvin-White fluid parameter in the energy function itself. So we have a Kelvin-White fluid parameter here. So what we saw is in the energy function, it decays exponentially fast as time grows. Okay. So what it implies is since the lambda appears in the numerator of the energy function, so it has a stabilizing effect basically.
Okay.
And we have a coupling parameters eta 1 and eta 2, so they help us to capture the nonlinear effects. So that is the reason we introduce eta 1 and eta 2 to choose the Rayleigh number optimally well, and as well as to capture the nonlinear effects.
Thank you.
Anyone else? Yeah, I really liked this nonlinear instability and stability that you worked on. So, how difficult was it for you to produce the numerical results for the nonlinear part?
I don't see much challenge in the producing the results, but the only challenge what I faced was proving the the stability condition and obtaining the eigenvalue problem from the nonlinear theory. Apart from that, if I see the eigenvalue problem, what I end up with, it is pretty much similar to the problem what we have in the linear theory. So it just need a computation of the Rayleigh number which satisfies this differential value problem. So I think we don't have much challenge, but the challenge what we have is proving it theoretically how energy decays or decays or like whether it decays or whether it not decays. So that's the challenge part, like compared to the linear theory and non-linear theory. So apart from that, like when it comes to the numerics, so they're pretty much same.
Yeah, so if I use the linear theory, how far I will be from the correct solution? I mean, I don't know basically.
Yeah, so from the linear theory, so what we can get from the linear theory is the threshold value to ensure the instability of the system. So that will measure like whether the fluid system is unstable or not. But when it comes to the non-linear theory, so we'll get a threshold for the stability. So that will determine the thresholds for the stability. So in the linear theory, we are missing like whether we don't have a thresholds or like we don't have a condition to say whether the system is stable or not. So we can say about the instability of the region, but not the stability of the region.
Okay.
Stability of the system, I'm sorry.
Yeah, okay. I thank on my own behalf and also on behalf of the organizing committee of AMSC. Had you been here, you would have been kind of given some kind of memento, but I don't know whether they are going to mail you or not. Anyway, so thank you very much for your time.
Thank you.
And
Thank
it's so
much,
late today. Yeah, so good night to one. So you take good sleep.
Thank you.
You have
Can
a
I-
meeting coming up.
Thank you, sir. Can I stop sharing, sir?
Yeah, you can stop sharing. Thank you so much.
Thank you so much, sir. Nice to meet you.
Yeah, me too. Hope I meet you there somewhere in Texas.
Oh yeah. Please come by. So like
Yeah,
if you come to-
Bhatto sir, he said he will come this year, but he had called me. I still have not been able to go there. Let's see if we go in meet. Okay, thank you so much.
Yeah. See you, sir. Thank you, sir. Thank you. Bye.
So Mahapatra sir, are you ready to share?
Let me see. Yeah, I'm ready to share, but let's see.
Professor Hafez, you need to wait a little bit because we wanted to start with Mahapatra sir, but he was delayed. So we started the second lecture.
I think why don't you go with him now, right now? Okay?
So let's see, we start with, you be online, if
Yes,
Mahapatra sir can start.
Okay.
So you will find some arrow share, so you can go and click there. You should open your file on the desktop, maybe it will be easier for you
My
to.
file is in the desktop, it is here.
Then you go to share, then I think the arrow is there. If you click, it should be visible.
Okay, let's see what this is. And this is the...
I feel so bad. It's so late also for you already, maybe 1 a.m. or something.
It's late, but we had a storm here. So
Oh, yeah. So
we
that's
had
why
a
you have a problem.
storm and we didn't have any internet for a long time. So let me see if I have. I put the share and presentation more.
When you are clicking the share, is it showing your desktop or some folder?
It's share. Can you see it now?
Yeah, it's coming. The outline page is coming. You can go back probably, then it will show the.
Okay.
Yes. Yeah, it's coming. Yeah.
All right. I think I can just. I have to scroll it because I don't think that the other one will work. But it's fine. I can just go ahead. I'll just give a very short talk so that it's. Is that okay?
That's fine. If you don't have any problem, we don't have any problem. We only need to see the slides, but maybe it's an additional work for you. Anyway, so I'll just take 1 minute before we start. So actually, I wish not to introduce Professor Mahapatra because he's so well known and so well qualified, and he's the main person of soil of Odisha. And as far as I know, Professor Mahapatra, I'm from IIT Guwahati. I remember you visiting IIT Guwahati, so I worked there. And Professor Mahapatra has been teaching and doing research for a long time in the USA. he has been working, or he's just retired. That's what I was told this year after giving a 41 years of service to Central University of Florida. And he is a very well-known name, not only in India, and he really loves India because I see his name in many conferences in India, whether it is offline or online. And we are really privileged to listen to Professor Mahapatra. And if you know, I mean, the time difference is probably 9.5 hours or 10.5 hours, so it's quite late there. Still, he's awake and he faced the storm, that's what he said. But we are really delighted that he is here, and he is so experienced, not only in teaching and research. He has more than 250 publications. So, sir, you may please start. So, if you don't mind, I'll let you know after it's close to half an hour because we have some other lectures also.
That's right. You just tell me when to stop, okay?
Yeah, thank you, sir. And please start.
I'm going to talk about the results on erasures and discrete Gable frames. Let me just tell you what happens when you have a signal and you want to essentially transmit a signal. It could be pictures, it could be sound waves that you want to send, or you are going to transmit videos. You would have to, when you are transmitting them, you have to transmit them in terms of either the basis functions, so that if it's a three-dimensional one, you want to send them in the x, y, and the z direction. What happens if you use the basis functions as the means of your transformation? Then if certain things are lost, suppose the y coordinate is lost, then it is difficult for us to reconstruct the signal. And because of that, we try to find out what would be a best way that we can transmit, but at the same time, we do not have to have a large number of linearly independent variables along which we can essentially start it. So there came what is called the idea of frames. And let me just start talking about frames here. And in a Hilbert space, so we start with a H as a Hilbert space, and Hilbert space could be the k-dimensional complex numbers, or it could be L2 space over the integers, or the L2 space over the natural numbers. And because it's a Hilbert space, it will always have an inner product. So inner product xy is defined as x sigma. If it is a dimension is n, then it will be I going from 1 to n, xi times yi conjugate, and the norm will be written down like this. Norm of x is equal to square root of x comma x. Every Hilbert space has an orthonormal basis. So if EIs are the orthonormal basis, then EIs will satisfy the EI comma EJ. This inner product will be delta IJ, and the span of the EIs will be equal to the Hilbert space. In the orthonormal basis case, a vector has a unique representation because the Hilbert space, the unit representation is given like this, and then it always satisfies a Parseval identity. The Parseval identity is norm x square is equal to this particular sum square, where the EIs are the orthonormal sequences. Now, what are the advantages and disadvantages of sending transmission through the basis? The advantages are there is a unique representation, because once you have a basis, then you can uniquely represent the signal. Then it is also easy to find coefficients using inner product, so that we can essentially find it out. But the disadvantage is, it is very sensitive to data loss. When you are transmitting signals, it goes through a medium, and when it goes through a medium, there could be a data loss. And once the data is lost, and you are using the basis functions, then you would not be able to reconstruct. How did we do when we did not have this theory? Is that we essentially use interpolation to reconstruct the signals. And there were some errors, but we just managed with that. But now that there is frame theory, which we can use so that we can essentially get rid of that particular problem. Another disadvantage is that it is difficult or impossible to find bases which satisfy additional conditions. So, for example, if the signal is such that it has some group structures, and then it is harder when you have basis functions only. Now we'll talk about the frames in Hilbert space. In 1952, this is probably the most interesting. In 1952, while working on a problem of non-harmonic Fourier series, Dauphin and Schaefer hit upon an idea that we can essentially have more number of linearly independent vectors than the basis and use that to essentially use that for sending transmitting signals. If we are able to have that, then if something is lost, say for example in a three-dimensional for a three-dimensional space, if I'm going to send signals along four linearly independent vectors, if one of them is lost, I can still reconstruct. So the whole idea was to have a certain amount of redundancy into this system so that we can essentially do signal transmission in an effective way. Now, although Dauphin and Schaefer talked about frames, the frames never were worked on until 1980s, when wavelets were given by the Buches, and the Buches came to what is called the Fourier frames. And since then, the frame theory has started as an independent area of research in functional analysis. Now, there are different kinds of frames which are there. Frames generalize the concept of a basis, but sacrificing the uniqueness of the representation, which is often unnecessary in applications. Now, a frame is a sequence of vectors xi in a Hilbert space which satisfies this particular inequality. This inequality, a norm x square is less than equal to this sum is less than equal to b times norm x square for a and b, which are positive constants. The a and b are called the frame bounds. The optimal a and b, the case is when a is going to be the largest or b is going to be the smaller. But then we know how to find those things these days. If a is equal to b, the frame is called a tight frame. If a is equal to b is equal to 1, the frame is called the Parseval frame, and in that case, norm x square turns out to be this. If norm of x is equal to c, then the frame is called a uniform frame. Now there are, I will only limit myself to this, but there are fusion frames, and now there is an interaction between the graph theory as well as the frame theory. But I don't think that we have enough time for this. In a finite dimensional Hilbert space, the frame is such that the span of xi, the xi from 1 to n is going to be a frame, then the span of xi must be equal to h. In a Hilbert space H, a finite dimension K, sequence xi is a frame if and only if the span of xi is equal to h. In other words, a frame is a spanning set which need not be linearly independent like a basis. Now, some examples of frames. In R2, 1, 0, 0, 1 and 0, 1 is actually a frame. And this is what is called a Mercedes frame. Is in R3, no, in R2 you have 1, 0, minus half, square root of 3 over 2, minus half, minus square root of 3 over 2. The frame is these three vectors. It is like the sign that you have in a Mercedes car, so that's why it's called a Mercedes-Benz frame. Now, infinite dimensional frames, let EI be an orthonormal basis for a Hilbert space H, then if Xi is defined as E1, E1, E2, E2, each of the orthonormal basis is repeated twice, then in that case it is a tight frame with A is equal to B is equal to 2. So we can actually construct frames like this. Now, in order to do analysis, particularly using frames for the transmission, what we really are interested in is to introduce two operators. One is called actually three operators. One is called the analysis operator, theta, which is a mapping from the Hilbert space H to the L2 space, and with theta x is equal to this. And the frame operator S, which is theta star is the adjoint of theta because it's a Hilbert space adjoint. So S is equal to theta star theta, which maps H to H such that the frame Sx is equal to this one. Note that the operators are defined for any sequence of vectors, but S is invertible if and only if Xi is a frame. The possible frame reconstruction is one of the most important features of an orthonormal basis is that for any x in H, x is equal to the inner product x comma EI times EI, I varying from 1 to k. Now, possible frame and reconstruction continues. One of the most important features of the orthonormal basis is that this representation is unique, and the possible frames can be used in this case. The possible frames also satisfy the reconstruction formula. The reconstruction formula is if FI's are the possible frames, I going from 1 to n, then x equal to this particular sum is a reconstruction formula. One has to prove that the reconstruction formula shows that x is equal to S of S times S operating on X, where S is the identity operator, S is the frame operator. So S is the identity operator if and only if Xi is a possible frame. So that was the frame operator. The reconstruction can be done like this. I just wanted to show that. To show that the reconstruction formulas, I have norm x square. I can write down the norm x square as x comma x. Then what I can do is to essentially have this x comma x this is going to be represented in terms of this. When Fi is a frame, then in that case I have the next sum which comes out. Then this is x comma Fi and Fi comma x. Therefore, it is going to be the modulus of x comma Fi square, and therefore the converse can also be proved in the same way as therefore it's a if and only if it's possible frame, the reconstruction formula works like this. The frame operator S is equal to A times the identity operator if and only if Xi is a tight frame with the frame bound A. Given any frame Xi, the sequence S to the S minus half Xi is a possible frame. Now, I want to tell you this is not the standard square root. It is actually the operator valued s minus half. Xi is a parsable frame. Then x can be represented in this manner. Then we can actually essentially reconstruct it. Now, then there is something called a dual frame. That means for a general frame, there is a similar reconstruction formula in this manner, and for each, given a particular frame, we can always reconstruct a dual frame, and the dual frame is given in this manner, and so in general, Xi is a frame for a k-dimensional Hilbert space H. Then there exists a sequence of vectors Yi such that for all x in H in the Hilbert space, X can be written down in terms of the sum I from 1 to n, the inner product x comma xi yi, which is equal to x comma yi xi. Then the yi's are called the dual frames. Now, we can reconstruction using dual frames. In general, if xi is a frame for a k-dimensional Hilbert space H, then there exists a sequence of vectors yi such that this series of inequalities, three equalities work. In particular, every frame xi has a dual frame given by S inverse xi, where S inverse is the inverse of the frame operator x. This dual frame is known as the canonical or standard dual frame of xi. Any other dual frame is called an alternate dual. So this is the canonical dual, that the other dual frames will be alternate duals. A frame has a unique dual frame if and only if it is a basis. Then the question is it possible to characterize all the dual frames? It's a natural question. Here is the orthogonal frames. If xi is a sequence in the Hilbert space H, I going from 1 to n, and ui is also a sequence. These are all frames for a k-dimensional Hilbert space H. Then this x comma xi ui, if this happens, if the x comma xi ui is equal to 0, and I going from 1 to n, x comma ui comma xi is equal to 0, then in that case, xi and the ui's are said to be orthogonal frames. So two frames, xi and ui, are said to be orthogonal frames provided this identity is satisfied. Now the whole idea of the frame theory is to have as many possibilities for us to transmit signals. The orthogonal frames characterize the alternate dual frames, and alternate dual is essentially alternate dual comes out as in this particular manner. Any alternate dual frame yi has the form S inverse xi plus ui, where ui is an orthogonal frame. The orthogonal frame is yi minus S inverse xi. S is the frame operator. Now, unitary representation and group representation frame. Let G be a group and H a Hilbert space. The set of all unitary bounded linear operators on H form a group, and a group homomorphism pi from G onto this group of operators is called a unitary representation. A unitary representation is called a frame representation if there exists psi in H which is the Hilbert space, such that pi g acting on psi, where G is in the group G, is a frame. In this case, psi is called the frame vector, and pi is called pi is said to admit a frame. Think of pi g as a homomorphism of the group. Now, the harmonic frame. Now, if n is a number less than m, and W1, W2, Wm be the mth distinct roots of unity, there are m distinct roots of unity, then eta k is equal to 1 over square root of m, and these n elements, these are n of them, W1k, W2k, and Wnk, where eta I from 0 to m minus 1 is a possible frame for C. This is called a harmonic frame. General harmonic frames are special, is a cyclic group. You see, what happens is that we have the frames, and the frames, these are called, these frames have the group structure, and this when it has a structure like this, it is called a cyclic group. Now, operator trace and dual frames. Let T be a linear operator on H, having dimension n less than infinity. Let k be greater than n, and L be a number greater than or equal to n. If EI, I from 1 to k, and VI, I from k from I from 1 to L are frames with dual frames, Fi and Wi, respectively, then for this linear operator, we have this T comma Fi, this inner product, is equal to T comma Pi Wi. This theorem is a little bit long to prove, and we are not going to prove any theorems here, but I'll just say that these theorems essentially tell us how the operator trace essentially works. Corollary is that for any frame Vi with dual frame Wi, the trace of the operator T can be written down in form of this inner product.
Sir Mahapatra, would you be able to complete in about 3-4 minutes?
Yes, sure. So what happens is that, so what I told is essentially you have we have frames are generalizations of basis vectors and have a certain structure, so that we can essentially transmit signals by that. Now, what is called an eraser? Eraser is when we, in the process of transmitting a signal, some data is lost. Each loss is considered as an eraser. Now, because the theoretical problem is, if there is one eraser in a frame of n elements, suppose there is one eraser, can we find an optimal frame? And the answer is yes. The theory is essentially goes very carefully into showing how you can essentially find if there is an eraser, we can still reconstruct, we can find out optimal frame for erasers, and we have also optimal frames of 2 erasers, then optimal frames for m. If in an n-dimensional space we have m elements missing, then we can also still construct it, and then we know how to do that. So the whole theory is a very long theory, and it can be worked out not only with functional analysis, it also goes into what is called operator algebra. Now I'll stop here.
Thank you very much, Professor Mahapatra. I'll just wait and see if anyone has any question. Audience, would you like to ask any question to Professor Mahapatra? None? Sector? No? Oh, okay. Yeah, it seems the audience, they don't have any query. So I, on my own behalf and on behalf of the organizing committee of this concern, would like to profusely thank you not only for delivering the lecture but also overcoming the problem that you had today, and it's so late for you also, so we apologize for that.
That's fine.
And actually everyone here, including myself, will be willing to see you in person in Orissa as well as in IIT Guwahati whenever you visit India next, sir. Please keep that in mind. And
Yeah, I will be coming in October. October I will be there in India. October to December 10.
October, oh, it's a long period. So would you have time to visit Guwahati as well? Then I can organize, arrange one visit
Yes,
for you to Guwahati.
send me an email and I will be able to visit.
Yeah, okay. Okay, thank you very much, sir, for your kind presence.
I will listen to the next lecture.
Pardon me?
I will listen to the next lecture.
Okay, yeah, you please be online. So I just thank you for the lecture. Yeah.
Okay, thank you.
Professor Hafiz, we have more than an hour. Yeah, so you are ready, right? I will just briefly introduce you. Professor Muhammad Ghulam Hafiz, he's from our neighboring country. So he is a professor in the Department of Mathematics of the Chittagong University of Engineering and Technology. And it seems he is also a visiting scientist at Bharatiya University, Coimbatore, on some ISRF project of DST. And he is basically holds his specialization in mathematical physics and plasma physics. And of course, for plasma physics and mathematical physics, the base is always mathematics. So I welcome you to the conference. It would have been much happier if you could have visited here. Anyway, so there is always a next time. So you may kindly proceed to share your screen, please. I will be here till then.
Okay. Just a minute.
Yeah, sure. So I am from Assam. I am much nearer to you than the people from Odisha.
Yes.
Are you finding difficulty in sharing?
No, just a minute. Okay.
And just a message for the other speakers for the next session. We started this first session little late.
So Professor, it's visible.
So for the other speakers for the next session, yeah, it's visible now. So for the other speakers for the next session, so we are running late by half an hour. This is just for your kind information.
Okay, thank you.
Yeah, Professor Hafiz, you may kindly start, and I'd like you to complete in about 25 minutes. I'll let you know. Yeah, thank you.
Okay.
Please.
Thank you. So good morning, everyone. It is a great pleasure to be here at the fourth international conference, a highly prestigious conference, and I would like to thank the organizer for inviting me to give this talk. And actually, I will talk about the nonlinear evaluation equation in plasma physics, starting from the basics of plasma, moving to distribution function and fluid model, and finally discussing how to derive the nonlinear evaluation equation and their application. That is why the title of my presentation is Nonlinear Dynamics of Plasma Waves in Space and Astrophysical Environment, Theory, Modeling, and Application. Okay, so plasma, actually, what is a plasma? Yeah, why it is unique? Why actually needs to distribution function to describe the motion of the charged particle, and how to derive the fluid model equation, and or how to derive the nonlinear evaluation equation from the model equation, and where the physical issue are applicable. That is why I will talk about this issue. So basically plasma is a fourth state of matter. Actually, plasma consists of plasma actually is a ionized gas, consists of electron and ion, sometimes neutrals. Yeah. So, as you know, is the fourth state of matter. Actually, matter does not like a material property. Actually, matter depends on the space scale and plasma properties. Yeah. So it is no 99% of the visible inverse in the plasma state. There is just a historical background of the plasma physics. I want to overlook this. Okay, so plasma exists in nature. All stars, including the sun, are in the plasma state. Yeah, where and in some of interstellar and intergalactic media also are exist in the plasma state. That is why most of the times researchers are says 99% of the inverse consists of plasma. Okay, so before studying to basic properties of plasma, what you know, one need to know the basic criteria of plasma. Okay, so by depending on the basic criteria of plasma, plasma can be classified in various types of plasma, because by depending on the degree of ionization, one can classify plasma say fully ionized or partially ionized, and depending on the field, one can also classify plasma as a magnetized plasma or unmagnetized plasma. And one more important thing, depending on the temperature and density, one can classify the plasma as a thermal plasma or non-thermal plasma. In thermal plasma, most of the time the temperatures are almost similar, but in non-thermal plasma, electron temperature basically sometimes greater than to the very greater than to the other plasma species. Okay, so. How to maintain the basic criteria of plasma? You know, plasma is electrically neutral to the outside. That means if the number of positive and negative charges equal in a sufficiently large volume for sufficiently long interval of time, actually this balance is referred to as the Cauchy neutrality. Okay, and the Debye length is very less than to the size of the plasma, and the volume must be very greater than equal to 1, actually, which is required to ensure the collective behavior and justify the statistical distribution for the derivation of the Debye length. Okay, so in plasma, basically many types of plasma species are supported. Some of plasma particle are heavy. That means have some inertia, but some of plasma particle have a inertialess due to the high energy. Okay, so to describe the inertialess charge particle, actually one need to use the statistical distribution. Okay, that is why one need to know the distribution function. Okay, so there are some distribution function. That means the thermal distribution function is the Maxwell distribution function, and some of other are non-thermal distribution function. That means the Kearney distribution function and kappa distribution function and Q distribution function. By using this distribution function, one can easily describe the motion of the inertial charge particle. Okay, so you know, plasma have a many degree of freedom. That is why one can study the waves in plasma. You know, plasma is a medium that can sustain both electrostatic and electromagnetic waves, and there are numerous waves that can be studied by instability using the harmonic wave analysis, and there are a lot of numerous processes which actually unstable mood that can saturate and attain large amplitude. When the amplitude of the linear wave becomes sufficiently last that in such situation one cannot ignore the nonlinearity. That is why nonlinearity contributes to the localization of wave and leading to the several types of coherent structure. And plasma is then support a wide variety of wave phenomena for understanding basically the interconnected set of charged particles which propagate in a periodically repeating fashion. And waves in plasma, in unmagnetized plasma, unmagnetized and collisionless plasma are most important actually for astrophysical and space plasma and existed in infinite ranges. Okay, so the collisional time, actually the collisional time between the charged particle is basically very long in comparison with the characteristics time scale. That is the inverse of the plasma frequency. Therefore, the plasma can be treated as a collisionless, and the collective motion of the plasma resulting in various types of wave and other types of collective phenomena. And since plasma have a many degree of freedom, that is why one can it can support various types of wave, such as ionoacoustic wave, where the ion inertia provided the driving force, and the other charge particle, that means inertial less charge particle are provide the restraining force by their pressure. And in this, in the similar manner, one can also study the positron acoustic wave, electron acoustic wave, and dust ion acoustic wave and dust acoustic wave. That means one can study various types of wave by the assumption of various types of plasma environment. Okay, so ionistic wave, it's actually the acoustic longitudinal electrostatic wave, low frequency wave, and the phase speed is must be larger than the thermal speed of the heavy particle, but mass smaller than the thermal speed of the lighter particle. That means inertial charge particle. And the resting force actually provided by the pressure of the lighter species, that means electron or positron, and the inertia is provided by the mass density of the ion species. And this is the purely longitudinal wave and governed due to the compression and rarefaction of the media. It's actually distinct, unlike the sound wave, because ionoacoustic wave may propagate in a collisionless media, because the ion interact with either electrostatic or electromagnetic field at large distance. Okay, so in the similar manner, one can study any other acoustic wave phenomena, such as electroacoustic wave phenomena, or positron acoustic wave phenomena, or dust ion acoustic wave phenomena. Okay, so since the ionoacoustic wave is supported in infinite ranges, that is why one can use the solitary wave theory. And soliton is a nonlinear and self-reinforcing localized wave packet that is strongly stable. It's preserved its shape while propagating freely at a constant velocity, and recover it after the collision with other such localized wave packet. And it is a remarkable stability can be traced to be a balance cancellation of the nonlinear and dispersive effect in the media. And shock wave, when the waves travel faster than the local speed of sound, they change the state of the medium through which they travel, and it's characterized by abrupt and discontinuous change in pressure, either pressure or temperature or density of the media. And the energy and speed of the shock wave and dissipating faster with disturbance, unlike solitude. And already the NASA already experimented found that the interstellar media support the collisional blow shock wave in the astrophysical or space environment. Okay, so how to derive the theoretical model equation under various types of plasma assumption. and one can study various types of plasma properties by deriving the mathematical model equation. Suppose one can study the motion of the individual charge particle under the influence of the electromagnetic field, and one can use the kinetic theory. That means one can develop the kinetical model to study the statistical description of the localization or velocity profile and their interaction with the presence of electromagnetic field. That means one can use the Boltzmann and PK equations to study the kinetical model. And since plasma have a fluid-like behavior, then one can use the magnetohydrodynamic fluid theory to drive the theoretical model equation, and one can also drive the hybrid model equation by combining the kinetic and the fluid model equation. Okay, so how to derive the fluid model equation based on the hydrodynamical fluid theory. Okay, so based on the conservation law, mass conservation law, one can easily derive the continuity equation, and momentum conservation law, one can easily derive the momentum equation. And since the charged particle either connected electric field or electromagnetic field, then one can use the Maxwell equation, and by simplifying the Maxwell equation, one can basically derive the Poisson equation. So the surface, overall surface, is bounded actually by the Poisson equation. So these are the fluid model equation. So one can use this fluid model equation to describe the physical issues in plasma environment under various types of assumption. Okay, so here I just display I just display a particular model actually to demonstrate the mathematical foundation, actually to demonstrate how to derive the mathematical equation to study the physical issues. That means various types of wave phenomena in plasma. Okay, so that is why this is actually the particular model based on the assumption of an unmagnetic plasma. Actually, this plasma consists the inertial charged ion and alpha q distributed electron and positron. That means here the ion have mass. That is why ion provide the driving force, and the electro and the restoring force actually come from the pressure of electron and positrons. Yeah, so the electron and positron are inertial charge particles. Okay, so to describe the motion of the inertial charge particle, one need to consider the distribution function. That is,
hello.
I have, yeah. So anything wrong? Okay. So in this situation, one can consider the alpha q distribution function for inertial charge particle, and since ion have some mass, that is why one can use the ion. Hello, anything problem?
Please go ahead. I think one of the online person is making.
Okay. Thank you so much. Since ion have mass, that is why one can apply the mass conservation law for ion. That means the equation one represent the continuity equation for ion, and the equation two represent the momentum equation for an ion. And since the charged particles are connected to the electric field, that is why by the Maxwell equation, equation 3, one can easily derive the equation 3. That means the Poisson equation. That means the plasma environment is bounded by the Poisson equation, and these are the actually normalized equation. It's the range of the plasma is very high, so it is very difficult to study in large range. That is why one need to use the normalization technique, and based on the normalization technique, one can easily study the physical issues of the plasma within a short range. Okay, that is why these are the actually normalized equation. So to derive, it is it is very difficult to solve the partial differential equation, not only partial differential equation, and very difficult to solve the set of partial differential equation. That is why one need to use the various types of mathematical technique to solve this fluid body equation. One is the perturbative method and another is the non-perturbative method. By using the non-perturbative method, one can use the arbitrary amplitude, that means the large amplitude of the acoustic wave phenomena, and by using the reductive perturbation method, one can study the small but finite amplitude acoustic wave phenomena. Okay, so here I just implemented the reductive perturbation method, and based on the reductive perturbation method, the stretching coordinate are for the dispersive media are considered as in equation 4, and for dissipative media are considered in 4. So by using the stretching coordinate as in equation 4 and the expansion of the Patar quantities as in equation 6, one can easily derive the various types of nonlinear evaluation equation, that means KDV equation. Okay. Since the KDV equation is integrable, so one can easily derive the solution of this equation by directly integrating, and which is very suitable for further experimental verification. And many researchers apply various types of mathematical technique to derive various a hang amount of solution by using various types of mathematical technique. Uh, but where the maximum time considers the nonlinear term or dispersion term or unity or any fixed value. But the nonlinear coefficient and the dispersive coefficient of the nonlinear evaluation are actually depends on the plasma parameters. Okay, so how to this parameter actually how to depends on the plasma parameter. Actually this the model equation is the normalized. Due to the normalized, one can easily determine the density ratio or temperature ratio, and based on the temperature ratio or density ratio, one can study the various types of acoustic various types of properties of the acoustic phenomena. That is why the parameter actually depends on the nonlinear coefficient, and dispersive coefficient actually depends on the physical parameter. Okay, so so based on the physical parameter, one can study various types of wave phenomena. Okay, so and this is the actually the solution, and based on the solution, the actually we just I have just displayed two figure. From this figure, it is clearly found that the both type of wave, that means rarefic wave and compressive wave, both type of wave actually are exist. That means there is a possibility one can determine the critical value, because when the nonlinear coefficient of the KDV equation is equal to 0, then the amplitude of the wave becomes infinity. That means which actually break down the validity of the reductive perturbation method. So to overcome this difficulty, one can need to reconsider the stretching coordinate or expansion of the Patar quantities, and by considering this, one can easily derive the more higher order nonlinearity involving any other nonlinear evaluation by involving higher order nonlinearity. That means the Cartesian equation with cubic nonlinearity. So one can easily derive the KDV equation with cubic nonlinearity, and this equation only applicable to study the acoustic wave phenomena around the critical value. Okay, so so to study the acoustic, that means acoustic wave phenomena, nonlinear wave phenomena around the critical value, one can only use the KDV with cubic nonlinearity. But the question is, when the when the nonlinear coefficient of both KdV equation, that means the nonlinear coefficient of KdV with quadratic nonlinearity and KdV with cubic nonlinearity are approaching to zero, then the validity of the reductive perturbation method is questionable. So,
Professor Hafiz, I'd like you to conclude in about 2-3 minutes.
okay. So
Thank you.
overcome this difficulty, one can derive the KdV equation with quadratic nonlinearity. Okay, so quadratic nonlinearity, and based on the solution, one can study the acoustic wave phenomena around the supercritical. Actually, this is actually the supercritical point where the nonlinear coefficient of both KdV equation is zero. That means which actually break down the validity of the reductive perturbation method. That is why to overcome this difficulty, one can derive various types of other nonlinear evaluation equation under various types of assumption. That is why there are a lot of scope. Still now there are a lot of scope to do further research work by deriving various types of nonlinear evaluation equation under various types of assumption or under various types of difficulty. In the similar manner, one can study also the shock wave phenomena. One can study also the shock wave phenomena in plasma, and finally the concluding remark I want to draw. Actually, there are still now so many possibilities to carry further investigation on the nonlinear wave phenomena, especially shock, solitary, vortices, and solitude. Also, double layer by proposing the plasma model. And one may also study the interaction wave phenomena by deriving the couple evaluation equation to study the silent feature of electrostatic resonances and their corresponding phase shift. And finally, the structure and properties of the plasma parameter effect on the solitary, not only solitary but also shock structure are still not clear, and a considerable progress in this direction can be achieved by undertaking a systematic study. And thanks to everyone. So, any question?
Yeah, thank you so much. I now just ask the audience if there is any question. So audience, is there any question from you? We have so many people working on plasma. No? I expected some questions. None? Yeah, I think it seems everyone has understood your lecture very nicely, so they don't have any query. So on my own behalf, as a session chair, and also on behalf of the organizing committee of AMSE, I'd like to thank you very much for your presentation. And overall, I would like to thank all the three speakers, and I see Professor Mahapatra is still awake. So Mahapatra sir and Dr. Basava Rajappa and Professor Hafiz for spending time for delivering lecture for this conference. So this is it from my side as session chair. I don't know if the I think the organizing committee member has something to say. Please wait for a while. Thank you.
Okay, thank you.
Thank you, sir. Thank you all my eminent speaker. Actually, we are running by late, so we now know tea break. So we will start our second session. And for second session, it is my privilege to introduce Professor Milu Acharya from Shiksha Anushandan deemed to be University, India, who will be chairing this session. Professor Acharya is a professor in the Department of Mathematics, ITR Shiksha Anushandan University. She received her PhD in complex analysis from Utkal University in 1997. With over 31 years of teaching experience, she has guided 13 PhD scholars and published nearly 70 research papers. Her areas of expertise include complex analysis, numerical analysis, operation research, fluid dynamics, and Fuzzy optimization. We are truly honored to have her as the chair of this session. I now request Professor Milu Acharya to kindly conduct and carry forward the proceedings.
Good morning, all. Thank you, Anuradha, for inviting me to session this chair. And now, from whom I need to start? It's the sequence I should maintain. Now I would like to introduce Dr. Kattar Ramesh, currently serving as an associate professor and deputy dean in the School of Mathematical Sciences, Sunway University. Yes. Professor Clemente Cesare, sir, you want to tell something?
Yeah, sorry. I have written an email yesterday. May I ask to Professor Ramesh if agree to change our talk because I have another meeting later. So if I can take now the talk and then we change with him, if it's possible.
Yeah, sure, Professor, no problem. Yeah.
Thank you very much. Really, thank you very much.
Okay, sir. Now I would like to invite Professor Clemento Cesarinos, who is the section of mathematics, Luciano Modica University, Italy. Professor Cesarino is the coordinator of the Masters in Applied and Industrial Mathematics and Vice Dean, Faculty of Engineering, who was a visiting professor at the Department of Mathematics, University of Turin, the member of Lepage Research Institute, and is the editor of several journals, as well as he's an editorial board member of the journal Research in Mathematics, and also the editorial board member of Carpathia and Mathematical Publications. He has published more than 250 research papers. Now the topic of his talk is Hermite polynomials in the description of Chebyshev-like polynomials. So now I would like to welcome Professor Clemento Cesarino to start his talk.
Okay, I can share the screen. Okay. You can see?
Yes, sir.
Okay. Let me know when I can start.
Sir, it's time we give you for 25 minutes. And after that, there will be a question and answer session for 5 minutes.
Okay. Thank you very much. So, thank you for this invitation to all the organizers of this very interesting conference, and thanks so much for accepting this change of talk pattern. So, thank you for Professor Ramesh. Thank you very much. Well, the title is a little bit changed. I mean, that is to be better to emphasize the role of the Hermite polynomials in the description of Chebyshev-like polynomials. And so the title is Chebyshev-like polynomials in the description of generalized Hermite polynomials. Oh, sorry, somebody. Okay. Well, what we can say, what we can do here, is important. I heard your voice. Is somebody speaking? I'm saying.
Sir, your voice is clearly audible.
Pardon?
There is no disturbance, sir. You can continue.
You can see it, you hear?
Yes, sir.
Okay, I can go on. Okay, as I said, we are talking about some modification and generalization of Chebyshev polynomial, I mean, in the sense of some part of this, and in particular in some technique of using of Hermite polynomial. The meaning of the paper or this talk that will be in some sense organized is try to use the concept and the formalism of some generalized Hermite polynomial, in particular the multi-index and multivariable Hermite polynomials, to define new polynomials of Chebyshev type. That is the sense. In much more detail is that we try to do something under isospectral methods. That means we use the operational roots of Hermite polynomials to use to generalize the Chebyshev polynomials. The approach is related to the technique of translation operator. I'm sorry for this mistake. That means that we have for an analytic functions, then we can use this expression to have a translation of the variable. That is it's a very standard and well-known relation. In this way, we used to say that this translation or shift is called shift or translation operator. And usually we do with exponential. That is one of the, of course, easy function to define. Okay, what we can see that if we apply this kind of operators in this sense with lambda a real parameter or real variable, it doesn't matter, then we have this shifting on this function if again we are considering analytic. And then in general we can write and we state this relation. Well, there are a lot of identities in this theory. They become from many old theory of the last century as well operator, Burknall operator, and things like that. So that just to understand which is the possibility that we have for this kind of shifting. But what is interesting is also the well rule for combine in some way the operator when we have two different operator of the same variable, x and they of the x, and so on. I mean, this is just the introduction of what we can do. Here, this is just more interesting, the Hausdorff identity. Then if we use again the exponential function, but we consider the m degree derivative, then we have this relation that looks like that, where m is a natural number, of course, and lambda is a real. But much more interesting is when we use the case m equal 2, then we have this that is always called the Hausdorff identity itself. We give other generalization, and then we see that it's possible to rewrite the application of the identity to have the power k for x. These are a lot of kind of identity. This, the last one, the exponential, where two exponents that does not commute, then by using this rule, we can obtain the commutator rule in this case. That is. So that what we do with these rules of translation or shift operators or things like that, why they are interesting? Well, they are interesting, but we can give us the possibility to introduce the Hermite polynomials from another point of view. That means is well known that Hermite polynomial could be defined by using a standard differential equation. We can define after this the Hermite polynomial as by using directly the generating function, or we can introduce Hermite polynomials by define directly their explicit form. In this way, by using shifting operator, we can do this. We define the second order derivative, capital D, then we apply to a function that is, in this case, x, essentially the monomial x, and then by using this, we immediately give this expression, that is Hermite polynomials of order of two variables. Then what we can do more? We can see that it's possible to obtain some very standard rule of Hermite that are well known in literature from more than 100 years, like this, and then we obtain the PD solved by this family of Hermite polynomials. But we can do more. We can read this PD as of D. I mean that we can use this partial differential equation in the variable y. Differential equation by this initial condition, and then we give us the solution of this that become an OD, linear OD in this form. So it's possible also to make much more generalization of this kind, and then we also derive directly the generating function that is well known. But the interesting part now is that we have started from a translation operator on the directly in the generative function. What we can do more? We can also use these techniques also to generalize more Hermite polynomials of other order. In this case, the HM polynomials of always order n. And in which way? Again, with using the same techniques of translation. And then here always T is belonging to R, the real number. Furthermore, we define a generalization of this PD, this partial differential equation. Again, we do the same trick. We read this partial differential equation only in the variable y, and then with this initial condition, we can state this operational identity that is the solution of this equation, read as ordinary, read linear, and then we give this. So that what we have to do now, the main part of this talk is related to the possibility to generalize, how we said it at the beginning, some class of the Chebyshev polynomial by use the formalism of the Hermite polynomials and much more the operational techniques that we have seen before. Let's start to see what we have to do. I go very fast here. X is a real number. This is a first and second kind Chebyshev polynomial of one variable. We can state the complex quantity, and then we give that the real part of this function is the first order Chebyshev polynomial, first kind, sorry, and this is first, second kind Chebyshev polynomials. Then we can derive generating function. This everything of in this slide is well known in literature. We can define also the explicit form of these two kind of Chebyshev polynomials. Then we can deduce the integral representation. What we do now? If these are the explicit form of first kind and second kind Chebyshev polynomial, we can remember that we can write the factorial of by using this expression of the exponential, and since this is the explicit form of this family of Hermite polynomial, then we can define this integral transformation of second kind Chebyshev polynomial in this form. And we can do exactly the same for the first kind Chebyshev polynomial T of nx. It is very easy to understand how is it possible, because we have just to make a manipulation of this expression. Then we can use this approach also to generalize this kind of Chebyshev polynomials, and then we can derive the Wn of x polynomials belonging to the family of Chebyshev, usually called in some reference as third kind Chebyshev polynomial, and then by using the properties of the Hermite polynomials, we can state many and many recurrence relation. I just put here some of much more interesting, but there are in literature also defined in some paper with my name this kind of relation that is possible to derive. But what we can do more? The interesting part is how we can use the previous defined Hermite polynomials of Gull-Doppler type of two variables in the context of Chebyshev. That is, we use this polynomial and we define a two variable generalized Chebyshev polynomials. We start with the second kind Chebyshev polynomial. We define this polynomial directly of two variables and one parameter. Here is always the mistake, is a real number. And then we do this directly on the integral representation that we have seen here. We start from this, we have a modification of Hermite polynomials, and then we define directly this kind of polynomial. Again, we derive many recurrence relations of this kind that are very useful for operational methods. And then we can also define a second order partial differential equation that, again, with the same trick, by using x as constant and holding the variable y, with this initial condition, we define this other relation. And so on. We do this for other polynomials, with the same for the first and third kind Chebyshev polynomials. This is the first part that is possible to derive from Chebyshev polynomial by using Hermite polynomial. But it's possible to do more. That is, we can use the operational techniques of Hermite polynomials to have a different generalization of Chebyshev. And then we start in this way, directly on explicit form. We define this Chebyshev polynomial. I mean, we know this Chebyshev polynomial of second kind of two variables with this integral representation. again, with just the modification of the kernel of the integral by using Hermite polynomial. We do this for different relation that we have seen before, and then we can combine these relation. One is very interesting, is the first, that is we can read these polynomials with these other expression of two variable, one parameter. If you remember, you have n of x, y, and alpha with alpha parameter. In this case, alpha is equal to 1. And then we define also integral representation for this kind of polynomials. We do the same for the first kind. We do the same also for the third kind, if you want. It's not mentioned here. And so that we can go on to define and derive differential relation about these polynomials. So that what we can do now, and maybe it depends how many time I have now, maybe 10 minutes or less. Okay. Is
You can continue
interesting
for 5
also
minutes.
this.
Sir, you
How
can
many
continue
minutes?
for 5 minutes.
5. Okay, so the core of the talk, it was at the beginning this Chebyshev polynomial that we used to call Chebyshev-like polynomials. We start with the Hermite polynomials that we have defined before of order n. We make again this manipulation directly on the structure of Chebyshev polynomial of second kind. Again, here is a natural number. And then with just a changing of the kernel of the integral, the structure of this Hermite polynomial, we define this integral representation for this new class of Chebyshev polynomial that usually is called Chebyshev-like. Again, we can derive many and many identities with the same idea and the same techniques that we have seen before, but what we can, it is interesting to note, is that all the properties that we can derive for these Chebyshev polynomials are derived from the properties of the Hermite polynomials that we have used to define and then in the integral transform. This is the interesting part. And then we can go on with these techniques, with this approach, to do many and many other generalization of Chebyshev polynomials. But of course, must be a sense. This is not a stupid exercise to do this. We have to find where the Chebyshev-like polynomial could be useful to define. And one of these is the parabolic cylinder function that give us the possibility to derive other exotic family of Hermite that has been from Wunsch many years ago. But the very interesting part that I would like to suggest is that it's possible to define a different family of Chebyshev polynomial. You can see in the last row here, again, by make exactly the inverse of the other things, and then we define these kind of polynomials. So that some few reference, I mean, as a standard things is with Appel-Campbell-Fourier polynomials that we have derived all the theory. This is very interesting, the paper of Doppler related to this two variable, etc. And then there are some paper of mine that we have defined. So thank you very much.
Okay. Can we begin? Oh, okay, good. Okay.
Thank you, sir, for your wonderful talk. Now, is there any question from the audience? Sir, there is no question from the audience side. Everybody has understood what you have delivered here. Thank you, sir. Now I would like to welcome Professor Kata Ramesh, currently serving
Thank you
as
very
an...
much. Thank you to Professor Ramesh. Thank you very much.
Thank you, sir. So now I would like to introduce Professor Kata Ramesh, currently working as an associate professor and deputy dean at the School of Mathematical Sciences, Sunway University, Malaysia. With over a decade of dedicated teaching and research experience, Dr. Ramesh completed his PhD from Visvesvaraya National University Institute of Technology, Nagpur, India. Dr. Ramesh has more than 100 research articles in renowned international journals. He has evaluated several research papers, and actually the specialization of Professor Kata Ramesh includes mathematical modeling and simulation of biological flows of biofluids, nanofluids, hybrid nanofluids, ternary nanofluids, microfluids, computational fluid dynamics, heat and mass transfer, and magnetohydrodynamics. Now I would like to invite Professor Ramesh to deliver a lecture on the topic blood flow dynamics in stenotech arteries. Sir, please start your talk, and time is 25 minutes.
Sure. Yeah, thank you, Professor Miru Acharya, for kind introduction. So I can share the slides. Can you see the slides?
Yes, sir. Yes, sir.
Yes, thank you. And first of all, I'll thanks Professor Appledev for inviting me for this conference. So in this session, I would like to discuss some insights of blood flow dynamics in stenosis arteries. So here, I would like to discuss these things actually. So in the introduction, I would like to cover the introduction of blood and stenotic regions and other things. And in the second part, I would like to discuss about formation of the problem. Here, we have taken one of the problem, then we model the problem and how we solve those things. And later on, we discuss solutions and results. Then coming to the introduction, so actually, coming to the blood, so blood is consisting of different kinds of tissues or different kinds of cells like plasma, plasma, red blood vessels, platelets, white blood cells, and so on. So overall, blood contains like plasma 55% and other elements like RBC, WBC, and other things will be of 45%. So each of these things do their work in different ways. For example, RBC carries oxygen using hemoglobin and remove carbon dioxide. Then coming to the WBC, this is a part of immune system. It is defending the blood body against the infections. And coming to the platelets, it helps in blood clotting and wound healing. Then the 90% of plasma contains water and 10% remaining nutrients, hormones, and waste products. Then coming to the blood flow, actually, whatever we discussed about the thing is blood before. So now coming to the blood flow. So it is a circulatory system. Okay, blood movement is start from heart to the artery. Then from artery, the blood goes to the arterioles, and later it goes to the capillaries. Then later it venules and then veins, and coming back to the heart. So there is entirely purely a circulatory system from heart to heart only. So artery generally everything wherever the parts are there like artery, arterioles, capillaries, and venules and veins, they have different actions. For example, artery carries oxygen-rich blood away from the artery. Then veins return the oxygen-poor blood back to the heart. Similarly, capillaries are small vessels where exchange of gases, nutrients, and waste occurs between blood and tissues. Then coming to the arterial stenosis, actually, whenever the person is healthy, so the healthy person's artery looks like this. So there is no disturbance while flowing the blood. But whenever unhealthy habits, due to unhealthy habits like smoking, alcohol consumption, and other unhealthy habits, so some of the fatty cholesterol builds up in the side of the artery. Then gradually it grows. Then whenever it improves the growth, then the artery blockage will be there. So whenever artery blockage is there, so that leads to heart attack. Primarily, whenever it is starting the plaque inside the artery, that is known as atherosclerosis. Then whenever it is improving in the both sides or one of the sides, so that is known as a stenosis. That is called as, in normal sense, we call it as narrowing the arteries. So whenever it is increasing gradually, then we can get the chest pain due to the low oxygen, that is called as angina. Then whenever it is increases, then we get the heart attack. Then uh, it is completely blocked the arteries. So whenever mathematically we see the different types of stenosis, we have in generally as per the limitations of mathematics in cylindrical geometries. So there are different kinds of stenosis like cosine shaped stenosis, trapezoidal shaped stenosis, triangular, bell shaped, side shaped, and irregular shaped. So there are variety of different kinds of stenotic arteries. For example, we have seen here. So here one side is formed, and here two sides is formed like this. So as per the limitations of mathematics, we have chosen the symmetric kind of stenotic part in the arteries, but this is open or some part here in different shapes. So that is open problem. One can do those things. Then coming to the blood behavior. So blood behaves as a Newtonian fluid when it is flowing through larger arteries at high shear rates. And whenever it comes to the smaller arteries where the diameter is very small and the shear stress are lower, the blood exhibits non-Newtonian characteristics. Moreover, it is also characteristics of the blood, the fluid also, blood also. So we have different kinds of fluid flow models in fluid dynamics. So there are many. Out of those fluids, so Bingham plastic model, power law model, Caro model, Kazan model, Herschel-Berkeley model are perfectly suitable to the blood flows due to shear thinning and yield stress behavior. So there are some effects usually whenever any disease or stenotic disease also. So usually in the hospitals the physiologist or physiologists refer to magnetic fields like MRI and other. They refer to detect the disease. So there are many applications. So this magnetic field regulates the blood flow. So whenever we apply the magnetic field to the blood, uh, Actually, blood is due to electrical conductivity of plasma and paramagnetic properties of hemoglobin. Then MRI uses stronger magnetic fields to visualize soft tissues and blood vessels. And there are many other applications of magnetic field. Similarly, there are two kinds of radiation. Actually, this radiation is is help us to kill the cancer tissues. There are two kinds of radiations. One is internal radiation, other one is external radiation. So both having different actions, and overall, this radiation can be helpful to treat the cancer disease. So coming to the formulation of the problem, here before I discussed about some non-nutrient behavior of blood and magnetic field and radiation. So those effects have been used in this formulation. So we have considered a stenotic part region. This is the artery having some stenosis here. So the height of stenosis is delta. Then the length of stenosis is L naught, and this is the length here D. Okay, the stenosis starts after D. Then we applied a magnetic field V naught, and we applied some thermal radiation, and this angle is chosen as alpha. Since here in human body, usually the veins or vessels, blood vessels, and other things are not usually horizontal or vertical. Mostly, it is some inclination angle it is having. That's the reason we considered for alpha inclination angle. And here, blood is considered as the Kazan fluid model because it is existing shear thinning behavior as well as ill stress behavior. So it is perfectly suitable for blood behavior. So coming to the governing equations, any fluid flow modeling, we have to deal with these three equations. One is continuity equation, another one is momentum equation. If you want to talk about heat equation, that is known as energy equation. So coming to the momentum equation, here this is the standard equation for any fluid model. So where S bar represents extra stress tensor for any fluid model. So in this case, I considered a Kazan fluid model so that S bar represents that extra stress tensor for Kazan model, and F bar is body forces it existing like MHD effects, maybe porous effects, maybe and buoyancy effects like that. And coming to the energy equation, so TA is consisting of some external forces like viscous dissipation, joule heating, heat generation, and some activation energy kind of things. So these things will be considered in TA. So the entire expressions are given like for FB is given as like this. Here we considered a magnetic field effect, so J cross B, and electroosmosis effects also we considered in this study, and the buoyancy force is also considered in this study. So coming to the extra stress tensor for Kazan model, so equation number 22.4 gives us S bar for Kazan fluid model. Whenever the stress, yield stress, the pi is critical value of yield stress, critical value. Whenever the stress is up to the certain level, then only the blood movement starts. So in this case, after simplification of these terms, so we get mu as mu b times of 1 plus 1 over beta. Then coming to the magnetic field, so J cross B is noted as negative sigma B naught square q bar, where J is known as current density vector and B is applied magnetic field. Then coming to the Poisson-Boltzmann equation, can be denoted as 2.8, and after some simplification you with the help of dB Haeckel linearization principle, so we get rho E as this expression. Then coming to the radiation and joule heating, okay, these terms are there in the energy equation. So this is about joule heating joule heating effects, and this is about thermal radiation effects. So according to the Rusland approximation, QR can be represented as this one, and with the help of Taylor series expansion, T power 4 can be represented as like this about T naught. And upon substituting T power 4 here in the equation 2.12, the Q bar can be noted as like this. Then upon substituting all those simplifications in the basic equations like momentum equation and energy equation and Poisson-Boltzmann equation, so we will reach to these two equations 2.15 to 2.17. 2.15 is Poisson-Boltzmann equation and 2.16 is a momentum equation and 2.17 is energy equation. These are the dimensional boundary condition for the arterial walls and middle of the artery. Then, in fluid dynamics point of view, we use some non-dimensional quantities to reduce the system, reduce the complexity of the system of equations. So we use these equations to reduce those equations. So after non-dimensionalization, we get the equations as 2.19 to 2.21, along with the boundary conditions. This one. So coming to the equation number 2.19, it is a simple equation like modified Bessel's equations of zeroth order. So we can see solve easily with the help of a Frobenius method. But whenever it comes to 2.20 and 2.21, so it is a system of simultaneous differential equations. So it is hard to get the solution analytically. So one can use any method. So we employed homotopy perturbation method to solve this two system of equations. So coming to the 2.19, so as I mentioned, it is a modified Bessel's differential equation of order 0. So this is the solution with the help of a Frobenius method. So where I naught kappa r can be represented as like this. Then coming to the homotopy perturbation method for momentum and energy equations. So we construct homotopies like this 3.3 and 3.4. Where Q is known as the embedding parameter that lies between 0 and 1, and where NW and L theta and N theta and F1, F2 are represented as like this with the help of our mathematical model. Then here it is main important thing is we need to carefully choose the initial guesses for velocity and temperature, so that the boundary conditions need to satisfy these these expressions. So W naught and T naught can be represented as 1 over 4 R square minus R square. So here we consider as a power series expansion W equal to W naught plus Q W1 plus Q square W2 plus order of cube, and similarly for theta. So substitution of these things 3.7 3.8 in the non-dimensional system of equations here, so we get a first order system along with the boundary conditions, similarly second order system along with the boundary conditions. So upon solving those we can get W1 theta 1, W2 theta 2. So upon substituting those terms W0, W1, W2, similarly thetas, and applying limit q tends to 1 to the solution, we get this solution for velocity and temperature. So these are the some graphical representations of the model. So these are the some velocity profiles for various values of inclination angle, Eckhart number, Grashof number, and electroosmosis parameter. So whenever our inclination angle, whenever alpha gives us 0 means that is horizontal tube or horizontal artery. Whenever it comes to alpha equal to pi by 2 means it is a vertical artery. So meaning here whenever the tube or that artery going from horizontal to vertical, then the velocity is increasing in the middle of the artery. So all these figures have been plotted at exactly at the position of stenotic region. So similar trend is observed for Eckhart number and Grashof number. Whenever it comes to electroosmosis parameter, the velocity declines in the middle of the artery, and near the walls, the behavior is different. So these are the some temperature profiles for various parameters like Helmholtz parameter, electroosmosis parameter, Kazan fluid parameter, and radiation parameter. So by with the help of these three figures, so we can say that with increasing of these parameters, Helmholtz velocity parameter, electroosmosis parameter, and Kazan fluid parameter, the temperature rises, and in the case of radiation parameter, the temperature declines. So these are the some plots on velocity and temperature for different shapes, different parameters of delta. Delta means stenotic height, and similarly different shapes of stenosis. For example, delta gives us zero means there is no stenosis, normal artery, healthy artery. So in the healthy artery, so the lower velocities are observed. So whenever it comes to zero point 0.6 moderate, zero point 0.6 means delta 0.6 means it is moderately stenotic part. So very lesser amount of plaque is built in the near of the artery walls. So in that case, the velocity is higher, little higher compared to normal stenotic, normal artery. Then whenever it comes to 0.9, delta is 0.9 means almost it is near to close the artery. So in that region, the velocity is very higher. It is physically justified whenever the lower space is there to flow the fluid means that definitely we can observe the higher velocities. And coming to this picture, so this is about different shapes like blue color indicates bell-shaped stenosis, red one is triangle-shaped stenosis, and different shapes we have. So in this case, we can observe the highest velocities for trapezoidal shaped stenosis appears in the artery, and
Excuse
lower
me, sir.
velocities is
Sir, actually, we are running shortage of time. Please try to complete within 2 to 3 minutes.
yes, definitely sure.
Thank you, sir.
Yeah. So similarly, these are the temperature profiles for various values of heights of stenosis and different shapes of stenosis. And these are the some pressure gradient profiles for various values of Kazan parameter, Grashof number, Hartmann parameter, electroosmosis parameter. One can see like how the behavior is. Then these are the some impedance resistance profiles for various parameters, and these are the some streamline profiles for Hartmann number like magnetic parameter. So whenever we increase the magnetic parameter, the trapping bolus is reduced. So these are the some conclusions, and these are the some references which I used for this presentation, and. Thank you. And for early career researchers, whatever I discussed, those things about the stenotic part. In addition to that, in biological fluid dynamics, so some other portion is also there to focus on. So like a peristaltic motion. So whenever we eat something or we drink something, so the system the mechanism, these the walls of this stenotic walls of this esophagus uh, forming like area of contraction relaxation. So based on contraction relaxation, the food bolus moves forward. So this is also emerging area to focus on. There are many applications or many devices, the devices introduced based on this phenomenon like peristaltic pump, roller pump, and so on. So this is also a similar case to the stenotic arteries. So it is also not always symmetric based on the situation, based on the disease. There might be asymmetric directions, that might be tapered directions, there might be some having some ciliated walls to the esophagus and so on. These are the some areas to extend. Okay. Okay. Thank you very much for the.
Thank you, sir, for your wonderful talk. Any questions from the audience?
Yes, ma'am. I have a question. Am I audible?
Yes.
Sir, you take Kaizen model to find the extra tensor. Extra
Yes.
tensor. So I want to ask that can other models be taken like Herschel Berkeley, or how we find that which model suited best to find the extra tensor for blood?
Yeah, coming to the blood, actually, we need to think about two things. One is either at least one thing, okay, whether it is having a shear thinning behavior or yield stress behavior. If it is having both behaviors, that is good for that. As per my understanding, Herschel-Berkeley model is shear thinning as well as having some yield stress behavior, so that you can apply easily Herschel-Berkeley model for modeling the blood flow.
Okay, sir. Okay, sir.
Yeah,
Thank you, sir.
yeah, thank you.
Any more questions? Uh, Thank you, sir, for your wonderful talk. So now I would like to move on to the next speaker. The next speaker is, let us welcome Professor K.S. Nisar, who is a distinguished mathematician with a PhD and MPhil in applied mathematics from Aligarh. Hello, Professor Nisar is there? You
Yes,
present
yes.
there? Yeah.
Yeah,
Okay, sir.
I'm
Okay, sir. Okay, sir. Professor K.S. Nisar is a distinguished mathematician with a PhD and MPhil in applied mathematics from Aligarh Muslim University and currently serves as a professor at Prince Satam bin Abdulaziz University, Saudi Arabia. With extensive teaching experience and over 50 national and international research projects, his work spans from fractional calculus, mathematical modeling, AI, fluid dynamics, and more. A globally recognized researcher, he has been listed among the top 2% scientists worldwide by Elsevier and Stanford University multiple times and has received several prestigious awards, including Obada Prize and University Research Excellence Awards. He is also an editorial board member for numerous high impact fact journals and has published many internationally acclaimed means journals. And now I would like to uh, welcome sir to present his lecture on the topic.
Okay, thank you so much and a very good morning to all of you. Thank you for the introduction. Let me share my presentation here. Okay, I think it's visible now.
Yes, sir. Yes, sir. It is.
Yeah, yeah. So I would like to wind up within 30 minutes because I would like to discuss some recent trend in mathematical modeling and the computational technique. So I would like to, many recent conferences and my webinars, I used to discuss with this topic due to its importance. So here I would like to talk about the intelligent computing methods and mathematical modeling. So here you can see mathematical modeling and intelligent computing are two linked fields that are processed that are critical for tackling complicated real-world problems. One second, let me adjust my screen. One second. Okay. Okay, I think it's fine. Okay. Yeah. So, mathematical modeling is the process of describing, analyzing, and anticipating behaviors by constructing abstract representation of system using mathematical concepts, equation, and algorithm. In contrast, intelligent computing process data makes decisions and optimize solution using cutting-edge approaches such as data analytics, machine learning, and artificial intelligence. So that's why these things are very important, because nowadays the trend is moving to the machine learning and artificial intelligence. Already many papers are available in this direction, and further improvement can be done using different type of mathematical tools. And it has a wide range of applications in healthcare, finance, environment research, and many other fields, including energy and green chemistry, etc. So here I would like to focus on some discussion based on uh, diseases, or especially we can say the highly complex modeling, or we can say the infectious disease modeling or epidemiology. So intelligent computing means a design of computational intelligence paradigm based on soft computing environment is proposed for the researchers in the field of bioinformatics, represented with a highly nonlinear step and complex system. So our interest is to consider, the complex problem or highly nonlinear nature of the problem. Then we are interested to, consider such type of problem with the help of intelligent computing. So, that computational platform are explored to solve the nonlinear complex system associated with uncertainty and precision that we represented with ODE or PDE to analyze and interpret epidemics and pandemic spread pattern of high-risk disease. That means, there are different type of diseases like, COVID-19 spread, HIV infections, hantavirus model, HCV infection model, tumor growth model, etc. So all these type of problems can be, modeled and solved by intelligent computational technique. So you are familiar with mathematical modeling and its different applications in various fields. So here you can see the salient features of soft computing algorithm are novel application of bio-inspired and nature-inspired computing algorithm to analyze the dynamics of governing complex nonlinear mathematical models for future prediction and control of epidemic disease and feasible interpretation of the pandemic pattern of high-risk diseases. So here we can say that, sometimes mathematically we can predict some scenarios, or we can solve, or we can suggest some control strategies with the help of this type of computational algorithm or intelligent computing technique. So that is one of the features. And the COVID-19 spread, I told you before that, this type of diseases can be considered, and considering RAM and sinusoidal and pulsary activity with the strength of approximation theory in mean square error sense through supervised and unsupervised neural network based on nonlinear differential equation models. So here you can see the machine learning techniques like, the neural network, or there are different type of methods and different type of neural networks are available. And this can be used for local and global search, especially in global search efficiency for bio-inspired global search algorithm and local search efficiency of gradient-driven methods. Now here you can see, secondly, the establishment of the quality of optimal solution in terms of accuracy, convergence, and stability by varying parameters of inputs in the system models. So while we are using this technique, it can improve the accuracy or the study in convergence conditions or stability analysis. Okay, these methods are much better as the existing method. And the next, the validation of invariable correctness is certified through experimentation and statistical analysis. Like, there are different type of statistical measures, including mean square error, regressions, correlations. Many things are there. Based on your situation or your model, you can find all this, or you can do all these statistical analysis. in terms of indicators for the performance monitoring through the statistical averages, variances, mean absolute deviations, mean absolute error, root mean square error, and Nash efficiency, etc. So, there are many things can be done using this type of technique. So these are the main features of using this type of intelligent computing technique. Now, a design of neural network layer structure for the proposed epidemic biomathematical model is given in the following figure. So, I would like to discuss some figures here. Accordingly, other neural network structure can also designed and constructed. Okay. So here you can see the schematic diagram, or we can say the algorithm or flow chart, or we can say the design of neural network structure for the problem will be like this. So what is the things here? Here you can see first we are going to develop the mathematical model for any epidemic system, or we will consider a complex model for the epidemiology. Then after that, we will design the model, like, sometimes we are using SIR, SITR, or SIER. There are different type of models. After that, this ODE system representing the epidemic model. So this is the first stage, the development of the model based on your situation. And you can see here susceptible and infectious. After that, T means under treatment people, and R is recovered. So this type of block diagram we have here. Now after that, what we are doing, we are considering the reference data set. Means the stage of our numerical method for generation of data set. So next stage we are going to generate the data set, and after that we have to use the intelligent computing infrastructure to solve the biomathematical real system, develop the epidemics and diseases. So here an example I would like to give here. We can say the system here as a mathematical modeling, and with different conditions and parameters are here. So we are considering this model, and after that we are using the intelligent computing technique like neural network. That means what we do next, we will design the neural network layer structure for the proposed epidemic biomathematical models. Then application of bio-natural inspired computing algorithm and analyze the dynamics of governing complex nonlinear mathematical models. So after designing the problems, yeah, first after designing the problems, we will consider the reference data set, and after that we will implement, or we will analyze the result with the help of some ML technique, or we can say like ANN or other type of neural networks. Finally, we will have the statistical analysis, or we can say results and analysis. And here we will have the different scenarios like accuracy, convergence, and stability by varying parameters of in different systems. Now, after that, we will do the statistical analysis like mean square error, fitness, regression error, and statistical measures of all variance. Now here you can see the schematic diagram of the neural network. So here you can say we have the input data here, okay, and the process is going here inside. That means by considering different type of neurons, or we can say the layer of neural networks, or we can say different type of networks are there with the weight of HZ, and after that, we have the output data for the epidemic model. So this is the process. Okay, that means we have the input data, and there are some, layers of, we can say that the neurons. And after processing this, we will have the result that we call that output data. So like this one, you can see, you can find the different type of data. Okay, and by train and test the data, then you can validate the data by fixing different type of different number of neurons. So there are different type of intelligent computing technique or data-driven model. So I would like to discuss something just to encourage you how we can work in different field. So this I would like to show some work related to this type of intelligent computing, and finally I will show you how these things are interrelated. So here I told you that for data-driven modeling and machine learning, we have different type of models like hybrid models, surrogate models, and explainable artificial intelligence. So in the hybrid model, what we are going to do, we are combining the traditional mathematical model with machine learning technique to improve the accuracy and predictive power. For example, integrating differential equation with a neural network. So this is one of the recent trend. Many people are working in this direction, and the results are much better as compared to the accuracy, or we can say the prediction. Now, surrogate model means using machine learning to create a simplified, computationally efficient model of a complex system. So here, what we are going to do, we are simplifying the complex model. And explainable AI means developing mathematical framework to infer and explain machine learning models, ensuring transparency and trustworthiness. So this I am not much familiar with this, but this is one of my future plan to use this type of technique to solve the problem. So, like recently some papers appeared related to intelligent neuroevolutionary computing approach, and here we used to solve campylobacteriosis transmission. So here we use the neural network technique, and this campylobacteriosis, it is one of the illness, diarrheal illness. And in CDC estimate, USA, 1.5 million people in the United States get ill from the Campylobacter every year. So, studying this type of bacteria is very important. I think if we consider about our data, like Indian data, it may be much higher as compared to US. So here, I don't want to explain much thing, but here we use artificial neural network along with long sigmoid as an activation function. So here we consider different type of techniques like Adam numerical solver that we compared with our methodology. So here, this is the model. Okay, you can see there are 5 classes, and these are the classes of CBT model. That is here we consider the different 5 type of classes, and after that we have these are the parameters. I don't want to explain all these things because it's available in the paper. Just I want to show that in the solution methodology here we use this thing. That means the artificial neural network related to solving this type of problems. Okay. And also we use here, the necessary information is given in order to combine GA and SQP. That means we use genetic algorithm and sequential quadratic programming. So you can see, usually, people are doing either genetic algorithm or ANN or SQP, like, differently. But here different type of concepts are used to compare the result. So this is the flow diagram for this method. So here you can see SCIRC model, that is the problem formulation. I already explained to you about that figure. We have different type of steps. So first step is for problem formulation. Second one, formulation of the model. That means mathematical models for certain problems. After that, we have the technique. Okay, that is intelligent computing technique, like artificial neural network, log sigmoid, and properties of both genetic algorithm and SQR. So we used here, and finally you can see that the analysis of the result. So this is the structure. Okay, this is the structure, or this is the flowchart of the problem. So this way, you can see finally the result is some statistical analysis done with the help of fitness and all these things. Okay. Additionally, there are imaging and RMS, the root mean square error, and different type of validations are done. So like this. So in conclusion, that there is a effectiveness of this adjusted intelligent solver with a laying between the range this and that, and the performance convergence criteria, which are calculated for 100 runs, demonstrate how Well, the suggested solution meets the stringent criteria. Additionally, statistical explanations using 100 independent using MID RMSE indexes further validate the brilliance and their answers are precise between 6 and so there are some comparison or we can say some statistical way of analyzing the things. So just I want to say that this type of work can be done very nice. Okay. So here you can see it has a huge application. That means the computation intelligence techniques have huge applications in healthcare biology, including epidemiological models like I'll explain, personalized medicine. Okay, means models with tumor growth modeling cancer therapy, and system biology, that means modeling of complex biological system. So some example here, you can see new insight into disease dynamics and treatment intervention with PID control based on therapeutic strategies in pancreatic cancer. So like, this type of paper is easily getting accepted because, the content is directly connected to the UN program. So you have to focus this type of thing. Okay. Like health and well-being is one of the United Nations goals or objectives. Okay, there are, I think, different 17 that topics are there. So this one belongs to one of that. I will not explain much about this modeling, but I would like to show, the schematic diagram of this PD model with diffusion coefficient. So you can see, it's a little complicated. So that type of complicated problems we are solving very easily with the help of different type of computational technique. Now here we use some parameters and this and that. There are some models based on this and some conclusion. So I don't want to explain much about that type of result and all. So here, what's the importance? How we are using these things? So in this paper also we did many things. Like also another paper you can see. This is about again about the cancer treatment with a sustainable approach. Similarly, we can solve the problems using different type of study can be done for climate and environmental changes. Okay, so climate change prediction. Actually, all these topics are very important. That's why I'm always saying you have to be different than the usual way of thinking. Like because nowadays these things are much demanding like, green chemistry, green nature, or climate problems, sustainability model, ecosystems, okay, or we can say this EV models. So there are something, important to topic we have to consider. So here, this one is related to, chemical modeling. That means stability and chemical modeling of disparities in atmospheric analysis. So this is something related to this type of climate or environment research. And similarly, we can think about optimization and control engineering. So there are different type of engineering like smart manufacturing. So here also mathematician can do many things for optimization, predictive maintenance, and supply chain, and autonomous system, developing control models for autonomous vehicles, drones, and robotics. So, and energy system like solar grids and integrating them existing power network, etc. So, this way also we can think how to implement a different type of thing. So here you can see this model for the forestry resources conservation model. Okay, for toxin activity and human source of fire through modified cultures or ABC operation. So some of the work is directly connected to the relevance. Okay, and this is something called the all these are recent papers to show you how to connect these things with the relevant topic. And similarly, we have network science and complex system like the social network, infrastructure network, biological network, etc. So here also we can connect to different type of problems. Like here you can say SIQR model with human class and public awareness. And here it is related to the communication like unmanned aerial vehicle and related communications. It is in IEEE Java. And similarly, you can probabilistic model like robust optimization and random process. So those who are in statistical background, they can also connect to this type of technique with the real world problems. Okay, including financial market or weather forecasting. So these are very important, and it will have always important because the financial market will be there always. Okay, we cannot say that it is outdated. It will not be outdated. There will be a fluctuation. There will be a problem of currency depreciation, or there is a matter of inflation. I am very much interested in this field for the financial mathematics, economics, and all. So it's very interesting because you cannot predict the share market with the help of modeling. So still, there is a chance to explore this type of studies. And there are different type of currency in the world, and you can study its depreciation against the dollar, or like many things are there. And like weather forecasting also, nowadays very uh, big problem related to the global warming. So many things are there. So we can model this type of problem very easily. And another one, robust optimization. That means developing model that perform well under the range of uncertain conditions. And a random process. It is
yeah. Try to conclude within 5 minutes.
Okay. Then I will go to the end because okay. So, there are many other things like computational advances in high performance computing, like parallel computing, reduced order modeling, real time simulation. So there are, like support vector machine, different type of optimization techniques are there, like, support vector machine are there, many other, like random forest. So, mathematician can do many things with the different people like engineers, data science people, computer science people. So there is a huge hope in this direction. I already told you about I am much interested in economics and finance. Also sports analytics, applying mathematical model to optimize team strategies and play performance. So there are many different things are there. Now, those who are interested to collect the data or some other open source tools, they can use this, increasing use of tools like Python, R, and Julia for mathematical modeling, collaborative platform like GitHub, GitLab, and there is something University of California. So all these repositories are available for open source data. So this thing I would like to skip, and there are, you can see plenty of paper related to intelligent computing. So here genetic algorithm, sequential quadratic programming, neural network are used to solve different type of problem, including fluid problems. Okay, and here also you can see that this is an study of all problems with the help of artificial neural network. And this is the smoking model with the help of wavelet neural network. So in conclusion, what is exactly happening? Mathematical model means there are different type like data-driven, machine learning integration, explainable AI. Okay, and for this data-driven, you can see there are multi-step, multi-physics, and coupled system. In healthcare, like epidemiology and personalized medicine, climate, sustainability, and ecosystem, optimization, autonomous system, and energy system. Network means social network, biological network. So this is the conclusion of these techniques. Now I would like to show one of my recent accepted paper. Here what we did, I am just doing proofreading. Today only I got this. I just want to show that. Then I will stop. I need 2 minutes. Then I will stop. Because those who are working. So this one is regarding the thermal analysis of Williamson nanofluid in cone and wedge geometries and artificial neural network optimization. So here, what we did, we use the NN tool. Okay, like there is a tool called NN tool for MATLAB. Okay, so we use that tool and we compare the result with. You can see all this visualization are available, and it is very easy because using tool, just you click, you choose the NN method, it will produce a maximum figure. But other than that, you can see in the table there is a comparison with the existing method and the ANN. So you can find a different type of like here you can see. So this is a comparison of tables, okay, for cone. So here you can see BB P4C method, and here we have ANN, and we mention this error analysis. So nowadays, this many papers are appearing like this. So this is one of the techniques we can use to solve different type of model. So we use ANN technique, okay, and compared with this P4C method, okay, and we find the error there. We mentioned the error there. So you can see here in the conclusion, okay. So there are a lot of analysis are there. So in the conclusion, what we did here, this was required to scrutinize the incompressible bonded layer for mass and heat transfer performance. Williamson nanopod for via two different geometries, cone and wedge, with the focus of unpredictable both thermal and solution properties. So MATLAB advanced tools are used to analyze the set of nonlinear equation with the suitable boundary conditions and determine the graphite issues. Okay, the main resolution. So here we are just using the tool. I think further you can improve this type of thing by writing code or something like that. Maybe you can increase type of things in the future. So so just I want to say that okay here we use this type of technique to solve even fluid problems also. So there are many tables compare the different results and all. Okay, and here you can see it is not worthy that the result generated through ANN model are accurate and authentic. Okay, so this trained model can be used to generate the result directly for the model without using numerical scale. So you can see the use of N, and also the current study also described the comparative analysis for the numerical and N and generative result. So here you can see something we projected, okay, by considering some intelligent computing technique. So that is one of the recent paper from thermal analysis and calorimetry. Okay, I'm doing this proof. And thank you very much for giving me very less time. Yeah.
Thank you, sir, for your wonderful talk. Any questions from the audience? Thank you, sir. So we will move on to the next speaker. Professor Varshageji is an emeritus professor. Madam, are you there? Professor Varshageji?
Yes, I have joined.
Okay.
Yes.
Thank you, madam.
Can you hear me?
Yes, your voice is clearly audible. Professor Varshageji is an emeritus professor at Savitribai Phule Pune University, Department of Scientific Computing, Modeling and Simulation in Pune. She has 30 years of postgraduate teaching experience. Her research focuses on fractional calculus, fractional differential equations, and applied mathematics. She has 86 publications. She has guided 9 PhDs, and she has received numerous awards like an Indian National Board for Higher Mathematics Research Fellowship, a Commonwealth Scholarship to work at Imperial College in London, a visiting scientist at Stockholm University's Theoretical Physics Department, and V.K. Jog Award for Outstanding Contribution to Research and Teaching. Her name is listed in the top for 2% scientists, and for today's talk will be on the fractional order dynamics, challenges and future directions. Madam, time is 25 minutes. Please start your talk.
Yes. Yeah, it is my pleasure. Am I audible?
Yes, ma'am. Yes, ma'am.
Can you see the screen? Is the screen?
No, madam, it is not free.
I mean, can one see my screen? I'm sharing my PDF file.
No,
Is
it
it
is
not
not
visible?
No, madam.
No, I have
Now it is
shared. I
visible.
have clicked this button.
Excuse me, madam. It is visible now.
It is visible. Should I get going? It gives work in this organized by Shiksha Anusandhan Bhuvaneshwar. I am thankful to the and Professor Apur Dev. Huh? Is it visible, my
Yes, ma'am.
slides?
Yes, madam. Your slides are visible, but your
Okay.
voice is not clear.
Huh. Okay. I am thankful to the organizers for giving me this opportunity. Today's topic is fractional order dynamics, challenges, and future direction. Is it audible now?
Yes, madam. Yes.
Ah, okay. So, plan of my lecture is here. I will give notations and so forth. So let me just quickly introduce you to the Riemann-Liouville fractional integral operator. It is given by convolution of the function with respect to this function x to the power alpha minus 1 divided by gamma alpha. So this is given by this equation. Am I audible?
Yes, ma'am.
You are audible, but slide is not moving. It is still in the first page.
Is it? Now I am on the second page. Is it there?
No,
Or
ma'am.
it is still the problem?
Yes, now.
How is working?
Okay. So this is the definition of Riemann-Liouville fractional integral operator, which is a convolution with respect to this function. Now Riemann-Liouville fractional derivative is defined as, so if alpha is between n minus 1 and n, then alpha is between n minus 1 and n, then this is the nth order derivative operating on fractional integral of the order n minus alpha. And Caputo fractional derivative of order alpha is you flip and take first nth order derivative, operate on that fractional integral. Now Riemann-Liouville derivative has its limitations, that Riemann-Liouville derivative of constant is not zero, and the initial conditions required for solving fractional differential equations have no physical interpretations. In contrast, Caputo derivatives require initial conditions in terms of ordinary derivatives, although the function has to be of class Cn. So to address these issues, modified Caputo derivative is introduced, where from a function you subtract this Taylor polynomial. Is my slide moving?
Yes.
Huh. And I'm audible also.
Yes, ma'am.
Thank you. So Caputo derivative of order alpha, where alpha lies between n minus 1 and n, is defined as from a function fx you subtract Taylor polynomial and then operate Riemann-Liouville fractional derivative. And this derivative enjoys the benefits of fractional Riemann-Liouville fractional derivative as well as Caputo derivative. Now, let us recall some facts about dynamical systems. So, this is the x dot equal to fx, where x is in Rn. This is a dynamical system in n dimensions, and a point E is called as equilibrium point if f of E, so if you substitute E, f of E is 0. Now, this is in general a non-linear function. So if you want to study the properties around the equilibrium point, what you do is you substitute, so you define xi. So xi is x minus E. So you linearize the system around the equilibrium point. So when I substitute dxi by dt, E is constant, so it is dx by dt. And I expand this around the fixed point E. So this is the first term and f of E is 0. So this term is 0. And then this is the df, the derivative term. So this is the Jacobian matrix. So in short, around equilibrium point, you can linearize the system, and x dot equal to fx you can study by xi dot equal to j xi, where j is the Jacobian matrix. Now consider the linear dynamical system x dot equal to ax, where its solution is given as e to the power ta, where a is matrix. So here you are exponentiating the matrix, and this solution x at t is equal to e to the power ta x naught. Now this e to the power ta is what is called as the flow of the dynamical system. So it satisfies this property that e at e raised to ta operated by e raised to sa is same as e to the power s plus ta. So this is called as the flow or semi-group property. Now I will compare this when I talk about fractional order dynamics. So just as exponentiation plays an important role in ordinary dynamics, a generalization of exponential function, namely Mittag-Leffler function, is important in fractional calculus. So it is defined by equation 5. So this is a generalization of exponential function. When you put alpha equal to 1, you recover exponential function. And two parameter function is defined like this. Now, a generalization of Mittag-Leffler function for matrix arguments. So just as you exponentiate matrix, here we have defined E alpha A, where A is a matrix, n by n real matrix. And you can show that this series is convergent absolutely for all square matrices in the uniform norm. Now, in our paper, we have shown that if A is n by n real matrix, then the initial value problem, which is given in Caputo fractional derivative. So here you have a system of equations where you have taken Caputo fractional derivative and A is a matrix, has a unique solution xt equal to, and the solution is in terms of Mittag-Leffler function. Now if you put alpha equal to 1, it will be, this right hand side will reduce to exponential function, and you have alpha equal to 1, this derivative becomes ordinary derivative and you recover your solution. But note here that just as you have a flow in traditional dynamics, here this exponential function doesn't satisfy this group property. E alpha T alpha A operating on S alpha A is not equal to E alpha T plus alpha A. Hence, the concept of flow cannot be defined for a general fraction order dynamical systems. Mittag-Leffler function also has another properties that, unlike exponential function, Mittag-Leffler function has infinite zeros. Now, here are the limitations. There in systems, the concept of flow cannot be defined, and therefore there is no Leibniz rule. So you cannot prove the theorems that are there in integer order dynamical systems, such as Poincare-Bendixson theorem, Hartman-Grobman theorem, and concept of phase portrait. So all these things cannot be extended to the fraction order dynamical system. But still there has been some progress, and it is first attempt was by Grigorenko and Grigorenko and their paper in Physical Review Letters, which has appeared in 2003, where they have considered fractional order Lorentz system. And here this is a fractional version of Lorentz system. Now they have shown that as you know, Lorentz system acts chaotic for certain parameters, and Grigorenko showed that when alpha 1 plus alpha 2 plus alpha 3 is they define call it as sigma, which is the sum of all these fractional orders, and when it is less than or equal to 3, you can get chaos. So interesting thing is, when this sum is less than 3, still you get chaos up to some value. And that value below which chaos disappears is called as the critical value. And voluminous work has been done to explore these fractional order dynamical systems. So we have explored fractional version of Bhalekar-Gaggi system, Lorentz system, Liu system, and so on. So much work has been done in this direction. Uh, Now we have conjectured. So as I mentioned that chaos disappears below certain value. We have conjectured that chaos cannot exist when capital sigma is less than or equal to 2 for fractional dynamical systems. So sigma equal to 2 is a global lower bound, and this is something like a generalization of Poincare-Bendixson theorem, which states that two-dimensional autonomous systems of integer order differential equations do not admit chaotic solutions. But here, this 2 is summation of alpha 1 plus alpha 2 plus alpha 3. Here note that these are fractional orders and capital sigma is not spatial dimension. So that is the difference. Now this conjecture has been published in this journal, Chaos Solitons Fractals. Now another concept that Grigorenko and Grigorenko have introduced, that they say that this they call it as a dimension of the system. But we have given an example here that we have considered fractional order chain system and consider the orders 0.85, 0.65 and 0.50. So one can see the summation of this is 2, and if you plot or simulate the trajectory, then you get a limit cycle. So you can see its summation is 2, but it is a purely three-dimensional object. So it is not a two-dimensional object. So sigma is not a spatial dimension. Now there are some results, especially important is non-existence of periodic solutions in fractional systems has been proven by Kaslik and Sivasundaram. So they have shown most differential equations does not admit non-constant periodic solutions. So this is important analytical result. Another thing is that consider fractional order autonomous dynamical system given in equation 9. Now the linearization of this around the equilibrium point E. So E is the equilibrium point. So f of E is 0. So we expand around and you get this non-linear term is replaced by Jx, where J is the Jacobian matrix. Now one can show that, we have shown it, that the solution of x equal to t is asymptotically stable if and only if all eigenvalues lambda j of the matrix, this Jacobian matrix, are greater than alpha pi by 2. And this system, the solution xt equal to e is stable if and only if all the eigenvalues satisfy this inequality. So this is the important fact that when you consider dynamic fractional order dynamical system, so this is the region if eigenvalues of the corresponding Jacobian matrix, if this region, then it is unstable region and this is a stable region. So if alpha is 1, this becomes a vertical line and you recover what you have in ordinary dynamical systems, that if eigenvalues have negative real part, so this negative real part is extended in case of fractional system, and here in this whole region is a stable region. Now with this we proceed further and define hyperbolic equilibrium point in case of fractional order dynamical systems. So when argument of the eigenvalue is not equal to alpha pi by 2, that means it doesn't lie on the cone. So this, if none of the eigenvalue lies on the cone and if it is not zero, then the point equilibrium point E is called as hyperbolic equilibrium point. Now, further we have studied fractional Hopf bifurcation. So as you know, Hopf bifurcation gives rise to creation or destruction of periodic orbits and leads to chaos. So we have given fractional Hopf bifurcation. So if you have a three-dimensional system, fractional difference consisting of fractional differential equations together with a bifurcation parameter nu, and suppose E sub nu is equilibrium point and the linearization of the fractional system around E nu is given by the 3 by 3 Jacobian matrix J. Now, if one pair of the eigenvalues must be complex conjugate of each other and lambda 3 is real, then we say the system undergoes fractional Hopf bifurcation if there exists a critical value such that argument of lambda 1 equal to argument of lambda 2 equal to alpha pi by. So it lies on the cone. Third value doesn't lie on the cone and d into is non-zero. So if it is satisfied, then we say fractional bifurcation has occurred. So Bhalekar Gauge system introduced by myself with my student is given here in equation 11. So what we have shown, we have studied it for these parameters and correspondingly we find the equilibrium points. So P1, P2, P3 are the three equilibrium points. Then we linearize the system around those equilibrium points. Now the Jacobian around P1 has the eigenvalues given here, and we can we can clearly see if B plus mu is positive, then this is negative, and omega is negative, and origin is a stable equilibrium point. The other equilibrium points P2 and P3 are satisfy this equation f lambda equal to 0. Now fractional Hopf bifurcation will take place when argument of lambda is alpha pi by 2. After doing this analysis, we come and we can show that when mu is positive, omega is negative, and either b plus mu is positive and alpha is greater than 2/3, or b plus mu is negative and alpha is less than 2/3, then fractional Bhalekar-Gauge system around equilibrium points P2, P3 have one real eigenvalue lambda 3 and two complex conjugate values lambda 1, lambda 2. Further, there exists Hopf critical value which satisfies the criteria for fractional Hopf bifurcation. Then we consider these two cases. Now, when alpha is greater than 2/3 and beta plus mu is positive, there is a Hopf bifurcation which is subcritical and the system becomes chaotic. And when alpha is less than 2/3, beta plus mu is negative, the Hopf bifurcation is supercritical and there is no chaos. So here we have simulated this system, and one can show that when A is exceeding that hope parameter, then you can just see that when A is less, the trajectory is nearby certain trajectory. One goes value of A increases, you will see it becomes it converges to first. It becomes after it exceeds the value H, you suddenly see up to this point it becomes a limit cycle, and suddenly when it crosses that particular value, it becomes chaotic. So it sometimes spirals around one point, sometimes on another, and you see here chaotic solution. In other case, this is there is no chaos. It is that is corresponding to local stable manifold. So when you have a hyperbolic equilibrium point in the linear system, then this E tilde S and E tilde S, so this is a stable set, this is asymptotically stable set. So if origin is hyperbolic equilibrium, generalized eigenspace, and this is the stable eigen. Contact with I think there is some network issue. So what is okay, sir. So let us end this session here. Contact Bosa, madam. Excuse me, ma'am. Excuse me, sir. Yes. Excuse me, ma'am. Good afternoon. This is Borsa, madam. This is Professor Borsa. No, ma'am. There is another query. Can I ask in the meanwhile? There is a problem regarding my presentation. Okay. Okay.
Hello. 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 Actually, the participants' presentation will start from 2:30. Yes, ma'am. That is completely fine. But my concern is, I had my name in the first list, which was released on, I think, 24th, right? But the list which has been uploaded on 27th, I can't see my name in any of the presentations.
Hello, ma'am.
Hello,
Hello.
sir.
Yeah.
Hello, sir.
So I think you have received your presentation link, which will start from 2:30.
Yes, I have received.
Yes, ma'am. Yes, ma'am. So if you receive a link and then it is your final presentation time and that is the final presentation link. Okay, ma'am.
Yes, so
Yeah.
that is fine.
So
But
no, no, there
27th
is
was a
maybe
list.
mistake, man. No issue. Your presentation link we have received. No, you join in that link, and that is the participation presentation link. That will start from 2:30 after lunch. Now the
Yes.
speaker's presentation is going on, man.
Only last question, sir. So my name was on 14th number. So is the order that will be followed?
Yeah. You follow that order, man.
Thank you so much, sir. Thank
Okay. And I think you received a mail from session course here.
From which, sir?
You have received from your mail from which from whom you have received your mail?
Sir, just a minute. I just let you know. Just a minute. Sir, he is Mr. Prakash.
Sorry, ma'am.
Mr. Prakash Ratha.
Yeah. He will contact you, ma'am.
Right. Sir.
Okay, ma'am. It will start from after 2:30.
Yes. Thank you so
Okay.
much.
Thank you, ma'am. Thank you. Yes. Yes.
I think Professor Barsage's network issue is there, so that's why she is not able to continue her lecture. So let us thank Professor Barsagezi, and I'm thankful to the organizing committee for giving me the opportunity to session this technical topic. So thank you all. Now I Anuradha to continue.
Thank you, ma'am.
Sto che che tu stare CPM into gate 3. Okay. It is from gate 3. Gate number 3. Buses will be there. Okay.
Thank you to our esteemed speakers for sharing their valuable insights remotely, and special thanks to Professor Acharya for chairing this session effectively. Thank you, ma'am. Now we shall break for lunch. After lunch, a local tour has been arranged to visit some of the beautiful tourist spots of Bhubaneswar. University buses will be available to take all the delegates and participants for the tour around 3 o'clock and gate number 3. Okay, at gate number 3, buses will be there. Join us for dinner around 7:30 p.m. No, dinner. Okay. Same venue. Venue is the same, and around 7:30. Okay. So with this, we come to the close of the today's session. Once again, I thank you all our speakers, session chairs, and participants for their active involvement. Thank you, and we look forward to your participation tomorrow in day 3 of AMSE 2025. The online parallel session for participants will be held from 2:30 p.m. to 6 p.m. All registered participants are requested to join their respective online session rooms as per the schedule. Now I request everyone, please come to the dais for a group photograph. All the delegates, participants, speakers, everyone. Please all of you join.